to show my, I see that demonstration of ekran is switched off. What can I do?
Can I deliver my presentation first, please?
Yes, you can share your PowerPoint presentation, sir, immediately. I can play way off of you if you are having any problem from your side.
Shall I now?
Yes, yes.
Yeah, just a minute, please.
Just you can share your.
Yeah, I shared, but I couldn't find the presentation page.
So do one thing, sir. Just you can find a file on chat box. You can send from here.
Yeah.
Just you can find in chat box. You can upload.
Yeah, I am trying.
Okay, no problem. Take your own time.
Just a minute. Good morning.
Good morning.
Can I share my presentation?
Yes, yes, sir.
Yeah, okay. But I think there is a problem at the connection. I cannot share my presentation.
Yes, good morning. Sir, just you can share your.
I click share screen, but I cannot share any item. There is a message on the screen, host disabled participation screen sharing. I think I am not able to share my presentation. There is a problem at the connection.
As for me, I am ready, but I see on my ekran announcement that an organizer switched off ekrans of the participants.
Yeah, okay.
What can I do?
I listen to you.
Actually, the host has to make you co-host of the meeting. So the host of this meeting should authorize all of us to one by one to share our presentations. If not, it's not possible. So it's up to them.
Yeah, just a minute, sir. Just a minute. Just there was error. We'll be recorrecting everything. నాకే వస్తుంది అప్పుడు మాట్లాడి ఇప్పుడు ఏం కాదు. First over.
Hello. ఇక్కడ ఆల్ పార్టిసిపెంట్స్ షేర్ ఉంది కదా అంటే రిక్వెస్ట్ అన్వర్డ్స్ ఎక్కువ పార్టిసిపెంట్స్ అక్కడ ఇప్పుడు ఇచ్చిన సెకండ్ స్పీకర్ చాట్ చానా నువ్వున్నావు కదా ఇచ్చిన అతను ఫస్ట్ జాన్ సురేంద్రకి ఇస్తాను అయితే ఓకే ఇచ్చాను
Yeah, please apologize due to this error. So meanwhile, we asked Dr. Ruben Mas. Yeah, Dr. Wesley, just you can play your PPT on the screen. If you are still facing a problem, just you can mail us your PPT. Just you can mail your PPT.
You asked me to send you the PowerPoint presentation, but there is no, I mean, I can do that, but also the only thing that you have to do is to make co-host to each of the speakers.
You don't find screen share on the screen? Share screen on the screen, you don't find?
No, I mean, we cannot share the screen because we have not the power to do it, because the only host of this meeting is John Surendran right now.
Yes.
So to share the screen, you should be at least co-host of the meeting. So this is the basis of
Yes.
Zoom. So I don't know. But the one that is the host, the only thing that you have to do is to go to the participants of the meeting, go to the name of the speaker, and just make it co-host.
Yes. Actually, there was a error, sir. Just to be for 5 to 6 minutes, we'll go into agenda. So please apologize. There was a error in the technical problem. Just give me just 5 to 10 minutes. We'll solve it, and we request to take only 5 to 10 minutes. We'll join the event again. There was a small error in the technical issue. Hello. Hello. So, meanwhile, we request Dr. Ruben Malasta from Balester from Inorganic Chemistry Department of Spain to start the event, sir.
Okay. So can I start?
Be online, just be online.
Okay, so if you want. So you will pass the slides as I told you, right? Because I assume that you are sharing my presentation.
Just be, sir. So, is Dr. Wesley, you can find a share screen on your screen? Share screen option on your screen?
So I cannot share the screen. So you are sharing my presentation from the file that I sent you by the Zoom. So you will. I should start. Should I start or what?
No, sir. Just Dr. Wesley is ready, sir.
Okay.
We have given option. After that, after stop, you can start your talk. Please apologize.
Okay. So.
Sir, Dr. Wesley, you can start your presentation, sir. You can share your screen.
You see my screen?
Yes.
Yeah, yes. So let me start from the Republic Buryatia of Russia, near the Lake Baikal. And you see my title of my presentation and the names of my colleagues. And let me to show some slides as introduction. Here you see a ternary system, and it's a simple construction is seen on this phase reaction scheme. It was investigated firstly more than 100 years ago, and the same authors of references 2 and 3 will be on these first slides. It's interesting that the same authors firstly showed this phase reaction scheme. They are in the reference 2. And later in the paper with reference 3, they showed some isoplace vertical section of this diagram. And you see here to the left below line as the border of three-phase region.
Sorry, but no, there is no screen sharing. We are not seeing your screens. You are not. We are not seeing your presentation. Sorry to interrupt.
I'm sorry. What may I do for it?
No, sir. Just you can.
I'm sorry. Now maybe I will try again. Okay. I will try again. Is it possible? Do you see? No.
Yes.
You now see my. I told that I start with first slide here, and I on the first slide show the phase reaction scheme for the simple ternary system, and it is interesting that more than 100 years ago it was explained the structure of the system, but in nowadays the same research team firstly published with reference number 2 this reaction scheme. We don't see here the 4-phase reaction and possibility to existence for the 3-phase region. But next pictures was taken from the paper with reference number 3, and we now see one of these isoplace. It means vertical section, and it is not explained possibility of existence 3-phase region below near the 0 temperature and 0 degree and above, and other next section with 2% of nickel is shows the same 3-phase region, and next slide with 50% of nickel is the same problem. So it means that we need additional tool to check the results of the investigation of phase diagrams for ternary systems. And here you see my aim to show new approach to investigate the multi-component systems. It was started in Donetsk, Ukraine, and now is continued here in Ulan-Ude, Russia. We will see space models for XY diagrams, 3D models, and 4D models for the XYZ diagrams. And we will see examples when space diagram is used as a tool for material science. Firstly, we informed colleagues about it, about our investigation at the International Conference of Calfat in 2009, and it was taken by the organizers to publish in the Journal of Thermal Analysis and Calorimetry next year. And we used the idea many times, showed in different types of models for phase diagrams of ternary systems like previous one and this one in the monograph of Vogel. I think you see surely the advices of Frederick Reins to use the different possibilities to build simple ternary diagrams, and I won't read it. I will show this idea in different type of diagrams taken from his monograph, and the same very known monograph of Alan Prince about alloy phase equilibria, and he advised here to use a good way of verifying the shape of different phase regions is to model the phase region from Pleistocene. We will hope to use for it 3D prototyping to produce the so-called exploded phase diagram. When we work with 3, 4, 5 component and more complex systems, it is a great problem to produce these geometrical models. When we have ternary system, it's possible to see a space model above left and its projection to the concentration triangle. To the right, we see only the concentration for the takes YZ diagram of the quaternary system, and don't see a real 4-dimensional model of this diagram. And as you see, it is the same topology for these diagrams, binary, ternary, and quaternary, but for 3D model, we have 28 surfaces, and 4D, 75 hypersurfaces. Here is possibility to see. Unfortunately, it doesn't work, the dynamics to produce this type of phase diagram with 2 polymorphic modifications of the component B. And our software produce vertical and horizontal mass balances for any kind of diagram which are built by means of this software. Here is the same, unfortunately it doesn't work to produce, maybe, I'm sorry, I tried. I think it will work. You see different points on the concentration triangle to the left, and to the right you see the vertical material balances. It means different temperature intervals. We saw the ratio for different phases. And here we see next type of mass balances, horizontal ones. On the picture below, we see this isoplex, Mn, and to the left, it is a section of different surfaces, and to the right, above, it is the mass balances for different phase regions in this temperature. Besides, it's possible to use these phase diagrams as a simulator of the experimental investigation. It's possible to simulate data spectrum below for these 2 some points on the concentration triangle, and vertical mass balances for these mixtures, for these alloys, And besides, not only simulation of data spectrum, but it is a simulation of electroconductivity. In this system, there are intervals here. It is intervals without melt, and then again after for phase reaction, melt is appearing, and we see a high level for the electroconductivity, and at last it again will goes and to the right we see the situation when a mixture was taken in the field, when this situation with melt appearance in some period existence is not possible. So main principles of the phase diagram computer assembling is that before they are proceeding with the assembly of a whole diagram, a space scheme for the mono and invariant reactions, three-phase region borders, are to be elaborated. It resembles the shell reaction scheme. Then the contours of the surfaces with the unruled nature are to be closed. On this stage, experimental data and thermodynamic simulation are used. Surfaces should be approximated as the minimal ones, like the soap films with the minimal area. When geometrical elements, points, lines, surfaces, phase regions are designated, their names should contain the meaning, reason of the designation. After the computer assembling, the space model of phase diagram is becoming a useful tool to solve the different applied and fundamental tasks of the material science. We showed here in some slides our work with the atlas of phase diagrams for lead-free soldering. It contains explanation for 53 binary phase diagrams and for 22 ternary phase diagrams. We showed by red the diagrams that are confirmed by our models, and by blue, dark blue, the diagrams with the problems. So here you see one of this diagram with problems, aurum vismut stibium, and the numbers below means that we use 35 dots, 96 lines, and 60 surfaces on the boundary of 22 phase regions. And as a result, when we worked with this model, we found then in this book, Atlas for the lead-free solders, some lines belong to different surfaces have been lost. It's possible to show by our software that here we show by red on the isoplus vertical section. By red it is lines for surfaces section by model, and to the left these lines and these surfaces is absent on the published materials in this atlas. To the right below, it is the same red for surface for a line on the horizontal on the isothermal section. Here we see again model as a place with different position on the concentration triangle, and by red we see again that our model help to find the problems with drawings in this book. Next system, Silver Kappa Stanum, is more complex. We see here 127 dots, 318 lines, 247 surfaces, and 88 phase regions. There are some four-phase reactions, non-variant. It is showed here, and now I will use other examples, not from the Atlas of the light-free soldiers, when information about these ternary diagrams was till 1990 was interpreted as a diagram of eutectic type, and next year's Dr. Samura from Japan found a binary compound, and in the next year, 1994, the same authors of first reference, it is here third reference, they the same published diagram, these two pictures of these authors with reference number first to the left and number third to the right. So it means that many problems exist for real systems and for the hypothetical, virtual too. This pictures above is taken from the monograph of Alan Prince, and to the right you see a red line that showed the red line, yes, showed that is absent. That is absent in the monograph for different types of a different topology of diagrams, but the same problem exists when this line really can connect the points and contour of the surfaces is absent, and below we see that we overcome this problem and worked with this type of surfaces. And here by blue in the center, you see that this line we used to get the contour, close contour of the surface. And here we see the problem when different information about diagram is very close to the component, and firstly we need we are to work with the prototype of the diagram when it is possible to save the same geometrical information, but to move dots, lines, surfaces, and to understand the structure of the diagram more detailedly. And this proverb is known in statistics, but well-known colleague from France, Marcel Gonescar, used it in her book, Molten Salt and Unecliptis Bulletin. All models are wrong, but some are useful. Some slides will show you that we have information from the by means of our models that we tractate as our part in materials genome initiative. Here is information about this genome initiative announced in 2011 by President Obama. And next slide informs that there are different meanings of different colleagues about this initiative, and in the center you see that Professor Hafid Arag from Algeria used this terminology, and really we will show next slides that Larry Kaufman is named as father of materials genome. Here is information about Dr. Hafid Arag, and he used empirical pseudopotential method, but in his page we see mistake even in this word. And Larry Kaufman, it is paper published when he was he has gone that materials genome was given a rather vague definition in US President Obama's announcement in 2011. We argue that the materials genome, analogously with biological genomes, should be defined as a set of information databases allowing prediction of material structure, as well as its response to processing and usage conditions. The material genome is thus encoded in the language of thermodynamics and kinetics, computer coupling of phase diagrams, and thermochemistry, calculation of phase diagram. As such, databases are major parts of integrated computational materials engineering. To identify in these areas where more research is needed under the banner of the materials genome. It's more some additional details about it, about genome inherent property, and genome thus is a set of information obtained by careful assessment of experimental and theoretical data from which certain conclusions about the material can be drawn. And we, by our models, we may show that in this situation, when this fragment, we see this fragment A, EAB, FS, A in the ternary diagram with incongruently melting compound R, and we may show by about vertical material balances that there are three different parts of this segment. It means that phase reaction is here when melt, and the component A as a reagent, and the B component and binary independent compound R produced. And on the next picture below, we see it that it is possible that three fragments below, please see 4 lines. I see it, 3 fragments of the field A, E, A, B, F, S. This one triangle E, A, B, F, K with microstructure when matrix plus eutectical crystals of A, and next type of triangle with matrix plus primary crystals of A, and between them there is a triangle where matrix plus 2 types of these crystals exist. So it may be shown in details, and it is found by means of computer models of this system, of this ternary diagram. And above you see that ADC here, it is the same type of diagram with incongruently melting binary compound lead-3 bismuth, and the next triangles are eutectic, and we may produce any visualization of section for this diagram. Next opportunity is possible to use by these phase diagrams when we may understand and describe and use interesting features of the 3 phase regions when type of reactions is changed, peritectic for eutectic and eutectoid peritectoid, and with two liquids the same is possible. And here is a more complex situation, the X diagram with invariant quasi-peritectic transformation. And in the above to the right, we see this blue line, and we see that it is changed. Firstly, ratio of eutectical crystals A is grows, but then reaction means for peritectic one, and in this temperature interval, it is used for the peritectic diagram. It is possible to show that this situation with the change of phase reaction time is possible in every three-phase region. And there are investigations when we found different analytical solving for these conditions, and we use different mass-centric coordinates for multi-component systems published in this paper below. And as a result, it's possible to show for sections here. There are isothermal sections for to the left for 1400, and to the right 1300 for the system titanium, iridium, ruthenium. And red lines showed that different type of phase reaction is possible between these components. To the left, we see 6 different ratios for this CR-R3, and to the right, we see CR-R3 and R3 BC. We see these phase regions. The same is possible to see on the vertical sections, but this slide showed other possibility to use our models. We see here 2 pictures. Pictures to the left is written in the monograph published book. But to the right, we see that experts of this well-known MSIT foundation produce this picture to the right, and we don't see the curve. It is to the left, but it's absent. And it means that even famous experts may produce the errors, and only only model don't take it. It's possible to see different type of crystallization fields and trajectories for phases when melt crystallizes. And here we compare information from monograph of Danek. He said that crystallization paths are rather complicated, and therefore they will be discussed here. But nearly 40 years previously, Palatnik and Landau showed 32 crystallization paths was shown. And here is our results. We analyzed surely the same 32 crystallization fields were received as in the book of Palatnik-Landau. But besides, we found that there are different 3 types of concentration fields, 2-dimensional, 1-dimensional, 0-dimensional, and some of them belongs to the neighbor fields. In the book of Palatnik-Landau, we checked and found mistake with some region where reaction minus L plus C to the left in the book and to the right produced by the software. And the software produced the same below tables for different type of sections, vertical and horizontal ones. The same section to the left and to the right, we see horizontal mass balances for the temperature with the section MN. And when we talk about real systems as this one, the same first type of diagrams for this system was produced in 2012. I'm sorry, in 1915, and the first reference is from more late. And usually when engineers for the industry, for the chemical application are grown, usually in the books, usually 10 crystallization paths are discussed. When we work with the model of this diagram, we may see that this diagram contains 117 fields of 2-dimensional. On the borders of them, there are 133 fields of 1 dimension, it means lines, and 45 fields of 0 dimension. So we have information about 325 crystallization paths and only 10 used in the books. Some information when we work with quaternary systems and different type of sections are used to find eutectic by more short way. I show you these results, and here is a slide when we may produce section in the literature. This diagram to the left, and in the center we see published variant for the section, and to the right it is right section, and really authors did the same, lost some lines here. And here you see that for the diagram with binary incongruently quaternary system, and for space, for dimensional space diagram with this type of binary system, we may produce to the section of 2 types of 3D section, and will receive the same. This section 2-dimensional was received firstly when 4-dimensional diagram was sected by horizontally, and here by vertically by 4 dots on the boundary of the tetrahedron. Here is the same information, and working with the real system, we compared the section from the by yellow color from the real publication. And so one more phase diagram space model is required on all stages of the system investigation. It accumulates huge information which is more accessible with its computer model. The system investigation cannot be considered as completed if its computer model is not assembled. Third, most important, the computer model is constantly improving as the new tasks are formulated. We worked in this conference from 2012. Our session is 11, phase diagram as a tool of material science. In 20,
excuse me, sir.
I'm sorry. Thank you. I think I said enough, and I may conclude. And here is last slide. Thank you very much. Thank you very much.
Thanks very much to Dr. Vasily for nice presentation related to the phase diagram for ternary and quaternary systems.
Yes.
Thanks
So,
again for nice
yes,
presentation.
I need small request from Dr. Wesley. Give share of, host option to Dr. Osman or Dr. or for me, Inovine meetings. You need to give the option, sir.
I'm sorry. Please repeat. I'm sorry for my
Actually-
problems.
Actually, you are the host for this event at present.
Again, I have problems.
Actually, you are the host for this event. Give a option to Inovine meetings or Dr. Osman as a host option, because you are the host.
I may stop. Yes, stop demonstration. You ask me to stop demonstration. You ask me to stop demonstration.
No, sir. Can you please
Not?
make a host to Inovine Meetings LLC? You can change the options. I have provided meetings host option to you. That is the reason you are sharing this, share the screen. So please make a host to Inovine Meetings LLC from your system. Right side.
I may stop demonstration. Yes.
Make a host. Host to Inovine Meetings LLC.
I stopped my demonstration. Thank you.
Please check the chat box.
Hello. So you can read from chat box. You can find from chat box. Personally, I have sent you privately. Make a host to meetings LLC.
Can I share my presentation?
Yes, you are.
Inovine?
Yes, Inovine meetings LLC. Just make a host. Just go to the more options.
I cannot share Inovine. I couldn't share.
Right side click చేయండి.
Sir, just go to the Inovine meetings. You can find a more option. You understand my point? What I'm saying?
Mr. Wesley.
Yeah.
Yeah, Dr.
What should
Wesley.
Yeah.
You can click on the Inovine meetings LLC.
Mute or mute.
You can
What
find
should I do?
you can find two options: mute as well as more. Click on the more.
Which I couldn't see the option more.
Actually, there are, you can find just to click on the Inovine meetings LLC. You can find two options. One is mute as well as other one is more. MORE, more. You can find more option. Click on the more option.
I couldn't see more option.
You
on
can
the
you
screen.
you can check. You can see the participants. topper will you can click on the Inovine meetings. Actually, there was an error, sir. That's why I'm requesting you.
Unfortunately, I couldn't share, and I couldn't see another option to share.
Actually,
Yeah, I'm speaking to Dr. Wesley.
Yeah.
Yeah, doctor. Uh, in Zoom option, can you please go down for the participants? In down, you will get the participants option. From the participant, you just click on Inovine Meetings LLC.
From the participant,
Yes, yes. Just first
Yeah.
click on participants.
yeah,
Yeah. After that, just click on Inovine Meetings LLC.
yes.
Yes.
Shall I
After
click?
that, you have. Yes, you will get the two options. Yeah, you
I
will get
click
more
the-
option. Yeah, you will get more option.
It should
From
be
that
Professor Vasily, no Professor Osman. Should change Professor Vasily. Should change the host of the meeting.
Shall
Until
I
Professor
click
Vasily doesn't change anything, Dr. Osman cannot share anything.
Yes, yes. Doctor, yeah, Dr. Wesley, I'm
Can
requesting
I
you to
click
change the.
Dr. Vasily?
Yes, yes. Hello, Dr. Wesley.
hello. Yeah, hello, Dr. Wesley. I send you the screenshot how to make the host for the Inovine meetings. Hello. Sir, we'll do one thing, sir. Actually, there was a problem from Dr. Wesley. He is unable to share the screen. So we'll take around 5 minutes break, and we will send you the new. Just we can rejoin again. Just 5 minutes. Meanwhile, we'll recorrect the error by the technical problem what we are having. Okay. Just for 5 minutes. That's it. Yeah, it's fine, sir. Thank you very much, sir. It's okay now. So no, next talk will be Dr.
It is not my
We will go.
presentation.
Actually,
Inovine,
yes.
it is not my PPT.
So I'll be giving option to you, sir. Will you share your PPT? You need to share me the option again after you're completing your talk.
Unfortunately, I couldn't. I cannot share.
Hello.
Hello.
Sir, please share your PPT, sir. Please share your to my mentioned email ID or WhatsApp number immediately. We didn't get your PPT. We request Dr. Osman, please share your PPT to our mentioned mail ID.
Unfortunately, I cannot.
You can share your mail ID through email. You can send through mail ID. We'll be playing.
I sent you my PPT with email.
Yes, you can send again. Meanwhile, Dr. Ruben Mas Balesta from Spain will be going to start his talk. Okay, will you agree?
Okay, if you want, I can start.
To the contact at Inovine, yeah.
Yes. You can send.
Yeah,
You can check the chat box. We have sent two email IDs. You can send to both me email IDs.
Yeah. Just a minute, please.
Okay, so if you want, I can start or I wait.
Yes, we need to get permission from Dr. Osobat.
Okay.
Sir, we'll go with Dr. Ruben, sir. Is it okay? If you agree, we can go.
Doctor, can you check your WhatsApp? You got Dr. Osman PPT.
Kindly check your WhatsApp number, sir. They have the concerned program manager is asking from.
No, already I have sent your WhatsApp. Kindly check your WhatsApp and share it Dr. Osman will start the session.
Okay. Okay, sir, just we can go with Dr. Ruben Master. Sir, you can start your presentation.
I can start, yes?
Yes, yes.
Okay, so let's see if we can. Okay, I will talk about covalent organic frameworks for photocatalytic applications. Please, next slide. Photocatalysis, actually, it's reactivity that converts reagent to products, but takes advantage of the energy of light. So to do that, we need photocatalysts. So please, next slide. Okay, photocatalyst is a substance that actually can work in two different ways. One way is just absorb energy and transfer this energy to a reagent to finally convert to product. And actually, what can happen also is a couple of electron transfer processes. One will be the reduction of one of the reagents, and the other one will be the oxidation of the other of the reagents. So the coupling will generate the product. Okay. Eventually, instead of having two products, perhaps sometimes what happens is that you have, for instance, a sacrificial electron donor just to close the cycle. Okay, next slide, please. Okay, so we have different possibilities for photocatalysis. So we have homogeneous molecules, so discrete molecules like ruthenium and iridium complexes. Also, we have some organic molecules that also can do the same thing, but I will focus in heterogeneous photocatalysis. So we have two possibilities in organic materials like titanium dioxide or some other stuff like cadmium sulfide. And also we can design organic materials. And I will focus especially in the covalent organic frameworks, which we can design and we can build just by designing the building blocks that will build up this material. So please, next slide. So please a little bit faster. Okay. So there is a difference between what is a covalent organic framework and what is a common organic polymer. So usually the common organic polymers are just monomers that ensemble in a linear fashion, and these linear polymers just ensemble just through amorphous structures. However, we have 2D or 3D organic polymers that can be crystalline just by ensembling the building blocks of the correct geometry. So you have in here just examples of a laminar of layered 2D crystalline material. So a special example of that is what we'll see in the next slide, please. Well, this is just, it can be two-dimensional or three-dimensional. Please, next slide. Okay, this is one polymer that actually we have been working in my lab for several years. Actually, you can see here that it's the result of the condensation of amines and aldehydes. So you have a imine, and actually this polymer is crystalline and also it's porous. But even more, if you can see in the next slide, you can control the microstructure. Please, next slide, please. Okay, so you can control the microstructure. Okay, you have up a three-dimensional structure, so you have nanoparticles, and you have down exactly the same building blocks. Depending on the reaction conditions, you can have just a laminar structure, so a layered structure, or you can have the layers that just condense into spheres. And actually, the properties of these materials, even though chemically are identical, actually can be different. So next slide, please. We choose this model reaction just to take a look at the different photocatalytic properties of these materials. So this is the oxidation of sulfides to sulfoxides, and actually to do that in a selective fashion is a relevant synthetic goal in chemistry. So let's see what happened in the next slide, please. Okay, so we look at the materials, and actually the three materials are active, but the more active one is the one that it's just the layered structure, and actually it's the crystalline layered structure. So, and actually we took this material as the model material, and we have seen how it is possible to do the sulfoxidation just through 2 different substrates. So actually it's quite wide, the scope of this reaction. So please, next slide. We have been interested on how these materials can work, and actually there are 2 possibilities, as I commented at the beginning. One possibility is photoredox process, in which the oxygen actually is reduced to superoxide radical anion, and actually the sulfide is oxidized to the radical cation, and the coupling of these 2 species eventually gives you an intermediate that at the end gives you the sulfoxide. But the very same intermediate can be formed just by direct reaction of oxygen, which is activated just by energy transfer. In the fact, what you have is the singlet oxygen that actually reacts with the sulfates, with the sulfide to finally give the sulfoxide. So the way how we can distinguish these 2 mechanisms is using, for instance, a specific scavengers for this species. Okay, we did that, and in the next slide, please, next slide, we will see the results of using one scavenger or the other one. Next slide, please. Okay, so you have seen here that if we use the scavenger specific for the radical anion superoxide, there is no quenching of the reaction. However, if we use the specific scavenger of singlet oxygen, actually what we see is a reduction of the amount of the product that we are forming. So what we see in here is that these materials work as energy transfer mediators. So we follow an energy transfer mechanism. Please, next slide. So from here, we can, please, next. Okay, so what we actually arrived to the conclusion is that what we have is just this way. So we have this material is excited, and the excitation of this material actually transfers energy to the regular oxygen to a singlet oxygen. And this singlet oxygen is what actually reacts with the sulfide to generate this peroxide intermediate that eventually evolves to the sulfoxide. Please, next slide. So, and actually, one important thing that we can achieve with photocatalytic materials is that we can have recyclability. We can just make a run, just remove the material and reuse this material in a next reaction. So in here you see the values of the catalysis after 9 catalytic runs. So this is very important because molecular photocatalysts actually are quite reactive, and and usually you cannot recycle this catalyst, and actually sometimes what you have to do is use a high loading of these catalysts. So in that case, we can have this recyclability. So it's a first example of a catalytic material. Let's see how we can complicate a little bit. We can have a more sophisticated design of a photocatalytic system. So please, next slide. So we decided to change the building blocks, and now instead of having just a electronic structure that is just delocalized in here, not only that, but also we added a building block that is photoactive by itself. This is the PTH, the phenyl thiazine, okay? So, and we incorporated this building block, which is a known organic photocatalyst, molecular photocatalyst, into a material. So we generated the trialdehyde and we synthesized the material, as we can see in the next slide, please. Okay, this is the material. So you can see here that we incorporated the PTH fragment, and also we can dilute this PTH fragment, or we can just combine this PTH fragment with a triphenylamine fragment, which has different properties. So, and we analyzed the properties of the purely containing just the PTH, we have analyzed the material that just contains the triphenylamine and also the combinations of these two building blocks. So the results are in the next slide, please. In here, so under the same conditions, you can see here that if you increase the amount of PTH, you increase the effectivity of degradation of two pollutants like the PBDE, which is the brominated compound, also Sudan red, which is the red line. Also, you can see that whenever you have more PTH, you increase the degradation of this pollutant. However, the methylene blue just follows the opposite trend. So it's better degraded when you don't have PTH and you have actually the triphenylamine. So which means that, without going to the details, is that we can design the material with different active building blocks, and depending on the substrate that we want to activate or the pollutant that we want to degrade, we can use one or the other material. So next slide, please. In the case of the PBDE degradation, actually, we also demonstrated that we can have recyclability, and actually we did it with the purely containing PTH fragment. So please, next slide. And we found that, and we wanted to expand the reactivity, the use of this material to other processes. So we decided to change the reaction, and we tried to change to go to the oxidative coupling of amines. And actually, we had good yields, but actually we observed that there is leaching. Leaching means that the material is just releasing molecular fragments to the reaction medium, and these molecular fragments is what is doing the catalysis, which is undesirable. We don't want that. We want that the material is the active. So we decided to change our design. So please, next slide. To change the design, first we analyzed what is going on actually, and the leaching comes from the reactivity of the amine. The amine is nucleophilic, and these nucleophilic amines actually can react with the imines of the material, so releasing this product. So the point is that we have to change from imines to other functional groups that just held together the material. So this is next slide, what we did. Okay, so one is based in hydrazones. You can see here is not imines anymore, and we also tried a new one. So a new alternative, please. Next slide. So, and this is a triazine-based material. So these two materials actually are more stable. But let's see what happened when we do the leaching test. So when we analyze the catalytic activity of just the solution after removing the material. So if there is no leaching, the activity should be zero. Okay, let's see. Because next slide, please. Next, please. So this is just the comparative of the materials. We have seen here that with the imine-based material, we have a 61% of activity after removing the material. So it's too much. There is too much leaching in here. However, when we go to the hydrazone-based material, actually we reduce to the half this leaching. So this activity due to the molecular species just released. And actually, when we go to the triazine-based material, actually what happens is we only have 10% of this reactivity, which is more or less the background reaction without catalyst. So we don't have leaching when we use the triazine. So we are keeping the same photoactive fragment, but we took care about the functional group that just condensates and make this material more stable, so more useful to be as a catalyst. So please, next slide. So this is the tendency, okay? So please, next slide. And this is the recyclability depending on what material we use. So you can see here that we can get a good recyclability. So after 7 runs, we can just take the material and use it again for a reaction. And with the material based in well, the CTF material, actually it's pretty good. and the hydrazone is not as good. And actually, the imine-based cough, as we understand, is the worst one, because actually we have this leaching. We are just chemically making a chemical erosion of the material. So we want to avoid that. So please, next one. Next slide. I mean, we are always interested in how the materials work. So once we localized the material that it's the idoneous one, so we analyze the experiment, and also we arrived to the conclusion that this one also works as a singlet oxygen, a singlet oxygenate. Okay, so next one, please. Okay, so we can do this. We can try different things. For instance, we can insert one platinum complex. In that case, that we have some experience in the group, that this is an efficient photocatalyst for aerobic sulfoxidation. So we incorporated that in a covalent organic framework. How we did that? So next slide, please. So we did what is engineering of the defects. So we incorporated that as a defect in the material. So we generated this metal complex with an aldehyde group. This aldehyde group can just condensate in that case, and instead of having just a perfect, well, we'll say like that, perfect material, in some points we have some defects in which it's just inserted this platinum complex. This is the way how we did that. So it's covalently inserted, okay? So we tried the catalysis of that. Please, next slide. And we have seen that it's much more active towards sulfoxidation. This is the same reaction that before, but now we are increasing the activity. So in less time at room temperature, that the effectivity is much more. Why? Because actually the main catalysis is generated, it's performed by the platinum complex. Please, next slide. Okay, and you can see here, this is a very important thing, because it's not just that it's more active. So also we compare with the homogeneous platinum complex, and we realize that the homogeneous platinum complex at the beginning can be more active than the material, but the homogeneous platinum complex just at one point stops and is not catalytic anymore. However, our material can be can perform much runs of this transformation, and this is because we are preventing the formation of nanoparticles of platinum, and we observe that. So we are just inserting that the platinum is just immobilized, and it is overstabilized, this platinum complex, so it can perform much catalysis. So please, next slide. So I mean, I just analyzed the mechanism of the sulfoxidation, and in that case, is a mixture of both singlet oxygen and photoredox. Please, next slide. This is not okay. Next slide, please. It's a mixture of that. And finally, I want to share with you our last experiments, in which we change again the design of the covalent organic framework, and in that case, we incorporated a phenanthroline fragment. This phenanthroline fragment can coordinate metal centers, and we tried this coordination with nickel and iridium. Please, next slide. Okay, we coordinated with nickel and iridium. This is a laminar complex. And next slide, please. And the idea is to make a dual catalysis. So I will not get into details of the mechanism because we don't have time, but the point is that iridium can make one function, which is the photocatalytic part, the part that takes the energy of the light and converts it into active species. And actually, this active species reacts with nickel at the end, just facilitating the coupling of the two reagents that we are using here. Please, next slide. So it's just the two material, the two metallic centers. So, and we just examine it, just the cough without metal, there is no reaction. If you have only iridium, there is no reaction. If you have nickel, there is no reaction. If you take the mixture of only iridium and only nickel material, there is no reaction. But when you have iridium and nickel in the same material, you have a very good yield of the reaction. So the point is that you need these two catalytic centers just working together in a close proximity. okay, in the same material. And this work for this reaction, and also we expanded the scope of the reaction. Please, next slide. And also we compare with the homogeneous system, because Molander, which is a very talented catalysis investigator, actually designed a homogeneous system. And actually we compare the homogeneous system with our heterogeneous system, and the yields of the heterogeneous system is always higher. Why? Because we are preventing mainly the activation of the nickel center, because the nickel center has a huge tendency to generate nanoparticles. Again, the isolation of the metal center just prevents this its deactivation. So we can design metal organic frameworks that actually contain metals that just make more active the metal center. Okay, so this is one example of that. So please, next slide. Okay, we did the same process with a different reaction. Again, we need the two metals in the same material. Next slide, please. A third reaction, exactly the same idea, and always the yields higher than the homogeneous system. So we need it together in the same material, and actually when they are together, this system is much more active. I mean, at least it prevents the activation of the catalyst than the homogeneous version. So please, next slide. So I want to finish in here just summarizing a few take-home messages. First, the simple imine-based COFs have some inherent activity for aerobic photooxidation. Okay, so we said that for sulfoxidation, and this is via energy transfer. But we can incorporate organic active fragments to these materials, and these organic active fragments increase the activity and allows us to explore new processes. We have to be careful, because sometimes we have to be very careful looking at the leaching. The leaching always should be tested, because the stability, it's an important issue in heterogeneous catalysis, and stability can be improved by careful shot. I'm finishing. Okay, just finally.
మీరిద్దరు అట్లా ఉన్నారు.
Preventing the complex deactivation, and also if we design the covalent organic frameworks with fragments that are ligands, we can coordinate these metal centers, and actually we can design even dual photocatalysis, because they can interplay together in a close proximity, so they can even work better than these two molecular fragments are just in the solution. So please, next slide. Next slide, please. Okay, those are the people that are working in the lab, and just in red are the two guys who participated in this work. So please, next slide. So, and this is just an advertisement that we are organizing a special issue on this kind of stuff. So catalytic applications of porous organic materials, not specifically covalent organic frameworks, but also other materials. And that's all, guys. So any question that you have, I will be happy to answer.
Yes. Any questions? Any questions to Dr. Ruben Mas-Peleste?
Thanks very much to Dr. Ruben for nice presentation.
Okay, thank you.
Yes. We want to complete on your topic. Thank you for sharing your tips with us. Looking forward to meet you again next time in physical events, sir. Thank you very much for your participation.
Thank you.
Now we asked Dr. Osman Adigözlü from Firat University of Physics from Turkey to join the event, sir. Please apologize as you are the second talk over this conference.
Thank you very much.
Yes, sir. You can start your presentation.
Thank you very much. Inovine, can I start?
Yes, yes, sir.
Yeah. Good morning, good afternoon, and good evening, distinguished scholars, speakers, and delegates of the conference. I am very happy to address to you in this important conference, Chemistry and Nanoscience. I believe that it will be held in a successful way. Thank you very much. Let me introduce myself shortly. I am a retired scholar after 45 years academic life. I retired 1 year ago due to the age limit of 67, and I am participating conferences by myself only. As you can see, the title of my presentation is Crystallographic Analysis or Structural Transformations in Shape-Memory Alders. This is a multidisciplinary conference, and I am sure you believe me that every scholar is not familiar as every subject of the science. Therefore, at the beginning of my speech, I'll introduce basic terms and definition related to shape-memory effect. Then I will explain experimental studies and experimental result on two ternary copper-based shape-memory alders. Next slide, please. Shape-memory alders have a peculiar property to return to a previously defined shape or dimension when they are subjected to variation of temperature. This behavior is based on the crystallographic transformations called multicyclic transformation and evaluated by the structural change in atomic scale. These alloys can be plastic deformed in the low temperature multicyclic condition and recover the original shape just by thermal means on heating over the various transition temperature after removing the external strain. Also, there is a material cycle between deformed and original shape on cooling and heating. Shape-memory alloys exhibit another property called superelasticity, which is performed by mechanical stresses in a constant temperatures. Therefore, these alloys exhibit dual thermoelastic and superelastic characteristics in memory manner. Basic illustration of this effect in spring-like materials is given in the next slide. Next slide, please. This is the main processes for the shape-memory alloys. This is the high temperature parent phase structure in the bond level. First step is the cooling the material below the material finish temperatures. With cooling, the shape of material doesn't change, but the material keeps the deformed shape due to the plastic deformation. Keep the original shape, but the crystallographic transformations occurs in the material. Second step is the deformation, which is plastic deformation, and the material keeps the deformed shape after releasing the external forces. And on heating, the materials recover original shape and cycle between original and deformed shape on heating and cooling. Next slide, please. Shape-memory I mentioned this part, please. Next slide, please. This is the temperature hysteresis of shape memory alloys. This is a high temperature. The materials is cold from the high temperature parenthesis region. On cooling, Martenslik transformation start at MS temperature, which is Martenslik start temperatures, and transformation is completed at the MF temperatures. On heating, reverse austenitic transformation start at AS, austenitic start temperatures, and completed at AF temperatures. Over AF temperatures, the materials are complete in the parenthesis structures, and below the MF temperature, the material is complete at the product martensitic stage. Next slide, please. This is the stress strain diagram of in the shape memory effect. First step is the deformation in the low temperature martensitic condition. This is also a stress strain diagram in the superelasticity. As you can see, at the early stage of the deformation, it exhibits elastic material behavior, and the martenstic transformations occur in the plateau region, and it completed, and after releasing the external stress, the material keeps the deformed shape due to the plastic deformation and recover the original shape on heating, and cycle between original and deformed shape on heating and cooling respectively. This is the stress strain diagram in the superelasticity. This is in the superelasticity, forward and backward transformation paths are different, and the hysteresis loops refers to the energy dissipation. Next slide, please. This is the stress strain behavior of shape memory alloys at a temperature between martensitic finish and austenite start temperatures. Stress strain profile exhibit different characteristics beyond the shape memory effect and superelasticity. Next slide, please. This is also another illustration of thermal and mechanical memory. In the shape memory effect, the material is deformed in the low temperature martenstic condition and keeps the deformed shape after releasing, and on heating, material keeps return back to the original shape and cycle between original and deformed shape on heating and cooling respectively. In the superelasticity, material is deformed in the parenthesis region, and releasing the materials return back to the original shape, exhibiting classical elastic material behavior. Next slide, please. Shape memory behavior is evaluated by the microstructural change in atomic scale or angstrom scale caused by internal stresses, where shape change occurs in macro level. Martenstic transformations occur in materials in thermal manner on cooling from high temperature parenthesis region, and it is characterized by change in the crystal structure of material. These transformations are lattice distorting transformation and occur as twin martensite with cooperative movement of atoms over very short distances on the order of angstrom by means of shear life mechanism. Twin martensitic structures also turn into the determinate martensites or reoriented martensite by means of strain-induced martensitic transformation, applying external stresses. Next slide, please. This is the high temperature parent phase structures of the material. This is ordered structures. In particular, shape memory effect is observed in the ordered structural materials. First step is the cooling the materials. With cooling, ordered parent phase structures turn into the twin martensitic structures by means of thermal induced martensitic transformation, and with the deformation in the low temperature condition, twin induced twin martensitic structures turn into the determinate martensitic structures by means of stress-induced martensitic transformation. On heating, after deformation, the materials return back to the original shape and cycle between original and deformed shape on heating and releasing. Next slide, please. This is the schematic illustration of superelasticity. As I mentioned, the material is deformed in the parent phase region, and with deformation, ordered parent phase structures turn into the determinate martensitic structures, and releasing the external forces, the material recover the original shape, and the determinate martensitic structures turn into the ordered parent phase structures. Next slide, please. This is the three-dimensional illustration of shape memory mechanism. This is high temperature parent phase structures, austenitical structures, which is ordered structures. On cooling, ordered parent phase structures turn into the twin martensitic structures. By the stressing the materials, twin martensitic structures turn into the determinate martensitic structures, and releasing the external stress, the materials keeps the determinate martensitic structures, and on heating, determinate martensitic structures turn into the ordered parent phase structures and cycle between ordered and determinate martensitic structures on heating and cooling, respectively. Next slide, please. I mentioned this information. Next slide, please. As I mentioned, superelasticity is also linked with stress-induced martensitic transformation, which is induced by applying only mechanical stress. With this stress, parent austenitical phase structures turn into the completed determinate martensitic structures, as in the deformation step of shape memory effect, and the determinate martensitic structures turn into the parent phase structures upon releasing the external stresses. The crystal structures cycles between the parent phase and structures and determinate martensitic structures on stressing and releasing, and stress-strain curve exhibit nonlinear behavior, and stressing and releasing paths are different, and hysteresis lobes refer to the energy dissipation. Next slide, please. This is the ordered parent phase structures, and ordered parent phase structures turn into the determinate martensitic structures by means of the stress-induced martensitic transformation, by stressing the material in the parenthase region. Next slide, please. As I mentioned, multi-state transformation is a first-order solid-state fast transition and occurs in a few steps with the cooperative movement of atoms in displacing manner. Therefore, these transitions have diffusionless character and product multi-state phase inherits the order of current unaustenitic phase. Mainly, multi-state transformation occurs into basic steps in the beta phase region. The first one is Bain distortion and second one is lattice invariant share. Next slide, please. This is basic beta phase structures. This first one is classic BCS structures. Second one is cesium chloride type superlattice structures. Third one is DO3 type ordered structures. Fourth one is also L21 type ordered structures. Next slide, please. Bain distortion is mainly effective in ternary coupled day-shaped monomer and this distortion is a homogeneous distortion and consists of an expansion of 26% parallel to the over one type axis called Bain axis and a compression of 11% parallel to the 1,1,0 type direction perpendicular to the Bain axis. An FCT unit cell is delineated as a first step in the matrix beta phase structures, and this cell undergo to the corresponding FCC lattice structures. Therefore, the selected FCT unit cell turn into an FCC unit cell by means of Bain distortion. Next slide, please. This is selected FCT unit cell, and with this deformation, FCT unit cells turn into the FCC unit cell by means of Bain distortion. Next slide, please. Second step is lattice invariances and occurs as multi-state variants on A11 type planes of Arsenault matrix, which is basal plane of martensites. These shares occur in two opposite directions, 1,1 or type direction on the 1,1 or type planes of current phase. The 1,1 or plane family represents 6 certain planes and totally 24 martensite variants occurs, and these planes are listed as follows: 110 minus 110, 101 minus 101, or 11, or 1 and minus 1. Next slide, please. Lattice invariant share occurs lattice twinning shares, and lattice twinning is not uniform in coupled day-shaped monomer alloys, and these shares cause to the formation of unusual layer structures. The 1,1 or type planes of parent phase, which is basal planes, and turn into the unusual layer structures, which consist of an array of closed pocket planes with the complicated stacking sequences called S3R, 9R, or 18R. Martensite depending on the stacking sequences on the closed pocket planes of the ordered lattice. The periodicity and for the unit cell is completed through 18 layers in direction Z in 18 are martensitic structures. Next slide, please. This is the stacking of the one monotype planes of parenthese structures, and stacking is as follows: A, B, A, B, A, B, A, B, and with stacking with the layers turn into the layered structures by means of lattice invariant shell in the copper-dash Shepmaveri alders, and stacking is A, B, C, B, C, A, C, A, B, A, and other in the 9R or M9R structures. Next slide, please. This is also another illustration of the formation of layer structures in the DO3 type structures of the ternary copper-dash Shepmaveri alders. Next slide, please. These are the basic information and definition related to the Shepmaveri effect and crystallographic transformation. Experimental studies were performed on two copper-dash Shepmaveri alders. You can see the chemical composition of these alders. First one is copper, zinc, aluminum alders. Second one is copper, aluminum, mangan alders. These compositions were selected in the beta phase ranging of the materials in the crystallographic diagram, phase diagrams. In this important, this transformation temperatures are important. MS is martensite start and MF is martensite finish temperature, which occurs on cooling. As you can see, these transformation temperatures are over room temperatures, and both of the alders are completely product martensitic state at the room temperatures. Next slide, please. For the experimental studies, specimens obtained from these alders were solution treated for homogenization in the beta phase field as following, and then quenched in ice brine and aged at room temperatures. These beta-tizing temperatures are 830 degrees for copper, zinc, aluminum alders, and 700 degrees for copper, aluminum, mangan alders. These temperatures are in the beta phase field of the materials. Further, specimens for X-ray examinations were prepared by filling the alders, and further specimens were sealed in evacuated quartz tube and given beta phase homogenization treatment at these temperatures. Further diffractorams were obtained for all specimens at the different stage of aging in long time interval. Next slide, please. This is an X-ray diffractoram taken from the copper, zinc, aluminum alloy sample after long-term aging at room temperature about 15 years after first quenching. As you can see, X-ray diffractoram exhibit superlattice reflections and this plane peak pairs are important in the copper-based yapmaları alders. These peak pairs are 1 to 2 202, 1 to 8 208, 1 to 10 to 10 2010, and others. Next slide, please. This is also another X-ray diffractogram taken from the second alloy samples after long-term aging at room temperature for about 5 years after first quenching. As you can see, this diffractogram also exhibit superlattice reflection. We can see this peak phase in the copper aluminium mangan alloy diffractoram. Next slide, please. A series of X-ray diffractorams have been taken from the both of the alloy samples in a long time interval, and some change have been observed in the diffraction angles and peak intensities and characteristics with aging duration. In particular, some of the successive peak phases have shifted toward each other. These successive peak phases provide this relation between Miller index. Here, N is for 18R martensitic structures. As I mentioned, this plane pair can be listed as follows. For 18R structures, these are 122, 202, 128, 208, 110, 2010, 040, 320, and others. At the long-term investigation, it was observed that these peak pairs come close each other with aging duration, and this change refers to the changes in the crystal structures of the material. Next slide, please. This change refers to the rearrangement of atoms in disordered manner in the martensites. The basal plane of martensites is subjected to the hexagonal distortion with the martensite formation, on which atom size have important effect. In case the atoms occupying lattice size lattices have the same size, the basal plane of martensites becomes regular hexagon. Otherwise, the deviations occur from the hexagonal arrangements of atoms in case atom size are different. In the disordered case, all of the lattice size occupied randomly, and atomic size can be taken approximately equal each other. In the disordered case, lattice size are occupied regularly by certain atoms, which have different atomic size, and basal planes deviated from the regular hexagonal arrangement of atoms due to the atom size differences. Next slide, please. This is the basal plane structures of the materials. With the martensitic transformation, this rectangular shape of the basal plane turns into the hexagonal shape. In the disordered case, we can take approximately each other the lattice atomic sizes, and regular hexagonal arrangement occurs. In the ordered case, the atom sizes of neighbors atoms are different, and deviations from normal hexagonal arrangement occurs with the martensitic transformation. Next slide, please. These are two electron diffraction patterns taken from both of the alloy samples. As you can see, both X-ray diffractorams and electron diffraction patterns exhibit superlattice reflections. Next slide, please. As conclusion, Chapman effect is evaluated by the structural change in microscopic scale by means of martensitic transformation. The fundamental structures of the beta-type martensite are orthorhombic closed packet structures, which consist of an array of closed packet planes in copper-based Chapman alloys. Sorry. The beta-type martensites have their layered structures and characterized by the stacking sequences depending on the order in parent phase. Copper-based ternary alloys have the DO3-type superlattice in parent outstanding phase, and following stacking sequences occur with martensitic transformation. The stackings are A, B, C, B, C, A, C, A, B, A, B, C, B, C, A, C, A, B, and periodicity is completed throughout 18 layers in the Z direction of the crystal. Next slide, please. It is okay. Next slide, please. These are the references related to the presentation. Next slide, please. Thanks very much for your attention.
Any questions? Any questions to Dr. Usman Hakrizal?
Thank you very much.
Any questions?
I have a question.
Yeah, please.
Yes. Very interesting presentation, a topic I'm not very familiar with about, but I was trying to follow the mechanism that you've described in terms of how this causes change in the shapes of springs. And the pictures that you show are as if the texture is more or less a single crystal, whereas presumably in the spring there is a polycrystalline structure. Could you just comment on the importance of the texture or any other factors that actually make this work?
Thank you very much, Dr. Geoffrey. It is a good question. The mainly Chapman effect is observed polycrystalline materials. Copper-based alloys have crystalline structures which consist of very small grains. The mentioned crystallographic transformations mainly occurs in the single crystalline grain, and totally with the lattice invariant shells, totally 24 martensite variants occurs in the crystallographic level. Also, there are three crystal axes. These are 001, 100, and 010 axes. Therefore, there are three main axes and three type main distortions occur in the crystallographic level. Also, there is every scientist, every engineer are familiar that there are an elastic limit in the elastic materials. Also, there is a strain limit in the shape memory effect. This strain limit maximum, the strain limit is maximum 8% in the titanium nickel alloys. This limit is shorter than that limit in case of shape memory alloys. If we exceed this strain limit, the crystal imperfections and crystal defects like dislocation, slips, and other crystal imperfections occurs, and these imperfections affect the quality of every material as well as shape memory material. Is it okay, Dr. Joffrey?
Yes, thank you very much. That's very useful.
Thanks to you.
Yes.
Any other questions, please?
Any questions? Yes, thank you. Thank you very much, sir. Thank you very much for speaking up in this meeting.
Thanks
and
again.
providing a unique perspective. Thanks again for sharing your tips with us. Looking forward to meet you again next time in physical event if everything goes well.
Thanks very much.
Yes, sir. Now we ask Dr. Joanna Dupucci from Institute of Nuclear Physics, Polish Academy of Science from Poland to start the presentation.
Good morning, ladies and gentlemen. I will try to share my screen. Is everything okay?
Yes, yes.
Okay, so good morning, ladies and gentlemen. First, I would like to thank the organizer for giving me opportunity to present my research about fancy shaped gold nanostructure for application in anti-cancer therapy. So first, I will be talk about the application of gold nanoparticles, especially in medicine and in pharmacy. Next, I will show the materials and methods. I will explain why I choose the gold nanoparticles, and I will show the synthesis of the nanoparticles and the mechanism of the stability of these nanoparticles. Next, I will show the results, which will be divided into 4 parts. In first part, I will show the gold nanoparticles with different shape, which we use in photothermal anti-cancer therapy. Next, I will show the differences in the dynamic of accumulation of gold nanoparticles with different shape in cells. Next, I will be talk about the gold nanosystem, which in combined with proton anti-cancer therapy gives very nice results in glioblastoma treatment. And the last part of the results in the last part, the results I will be talk about the gold platinum complex for proton anti-cancer therapy. And at the end, I will summarize my presentation. So gold nanoparticles have very nice features and properties which we can use in chemical, biological, and physical sensors in photovoltaics, for example, in photocatalysis. We can use nanoparticles in electronic devices, for example, with diodes and phones. Moreover, optical properties of gold nanoparticles we can use in nanoparticles fabrication, for example, in laser ablation methods. And what is very important for me, gold nanoparticles we can use in medicine and pharmacy, for example, in bioimaging, in drug delivery system, in photothermal therapy, photodynamic therapy, and combined therapy. And for these three kind of therapy, I wanted to obtain gold nanoparticles, which will be characterized by low cytotoxicity, biocompatibility, anti-cancer properties, and what is very important for photothermal and photodynamic anti-cancer therapy, which have a high conversion from light to thermal energy, and which absorb light with wavelengths between 650 and 900 nanometers. So why I choose gold nanoparticles? First, gold nanoparticles have a very high thermal conductivity, which I can use in photothermal and photodynamic anti-cancer therapy. Moreover, gold nanoparticles have anti-cancer properties, and they are biocompatibility. I can synthesize these nanoparticles in the laboratory condition. They are stability in water as well as in buffer solution. For example, in this buffer, which we use in culture cells. And what is very important, we can change the properties of gold nanoparticles by changing the size and the shape of these nanoparticles. So first, I will present the results which we obtained for gold nanoparticles with different shape, which we used in photothermal anti-cancer therapy. And in this experiment, I synthesized gold nanoparticles using seed-mediated methods. This method we can divide it into two parts. In first part, we obtain gold nanoparticles, which have a spherical shape and size around 10 nanometers. And in the next step, we obtain gold rod nanoparticles, which have different size, and the shape of these nanoparticles we can obtain because we used two chemical compounds, CTAB and silver nitrate, which react to each other and gives the bromium ions when blocked the growth of the nanoparticles in 110 direction. So in the literature, we can find information about influence of the changing the concentration of silver ions, gold nanoseeds, and pH and the pH of this in the solution. For the morphology and structural properties of gold nanorods. So if we used higher concentration of silver ions, we obtain longer gold rod-shaped nanoparticles. If we used higher concentration of gold nanoseeds, we obtain shorter gold nanorods, but these nanorods will be thicker. And if we change the pH of the solution, we obtain gold nanorods, which have a sharp end. But in the literature, I can't find information about the influence of the temperature, time, synthesis, and the reducer concentration for morphological and structural properties of gold nanorods. Therefore, I decided to make a synthesis of gold nanoparticles where I change the time reaction, the temperature, and the reducer concentration. So if I change the reaction time, I use the same temperature and the same reducer concentration. When I change the temperature, the time of the synthesis and the reducer concentration were the same. And when I change the reducer concentration, temperature, and the time of the synthesis were the same. So gold nanorods, which we can find in the literature, I obtain after 1 hour of synthesis. So first, I investigate the influence of the time for the morphological and structural properties of gold nanoparticles. And as you can see, time is a factor which control the shape of our gold nanoparticles. So when I stop the synthesis after 1 minute, I obtain gold nanoparticles with spherical shape, which have very similar size to these which we obtain in first block of the CD-mediated synthesis method. After 15 minutes, we obtain cubic shape nanoparticles, and after a half hour, 1 hour, and 2 hours, we obtain gold rod nanoparticles with irregular and regular rod shape. So we wanted to know something about the mechanism of the create different shape of these nanoparticles. And because, as you can see, after 2 hours, we obtain gold rods which have thicker ends, and these ends were rounded. So we made some control experiments, and we think that as the synthesis time increases, the CTAB and the silver nitrate solution are used. Therefore, we observe that our gold nanoseeds goes to the end of the gold rods, and the shape evolution of the gold nanoparticles as a function of the reaction time results from the presence of these two chemical compounds. And these two chemical compounds react to each other, leads to the formation of bromium ions, which blocked the growth of gold nanoparticles in 110 direction. So in the next step, we change the temperature of the synthesis, and as you can see, as the temperature of the synthesis increase, the size of the nanoparticles increase, the number of pores increase, and our gold nanoparticles become more crystalline. This is very important. We didn't obtain gold nanorods shape, gold rod shape nanoparticles, but spherical nanoparticles. Therefore, we made next control experiments in a lower temperature, but this temperature was a critical temperature for the CTAB molecules, which which the composition we observe in high temperature. Therefore, we think that as the synthesis temperature increased, the composition of the CTAB solution was observed. Therefore, the bromium ions were not created, so we didn't observe the block of the growth of the nanoparticles in 110 direction. And next, we changed the reducer concentration. And as you can see, we didn't obtain the rod-shaped nanoparticles, but we obtained the gold nanostars, which have the core with very similar size, and which have a different size of the star arms. And for the smallest reducing concentration, we obtain gold nanostars with the shortest star arms, and for the highest reducer concentration, we obtain gold nanostars with the longest star arms. So for these nanoparticles, we also wanted to know something about the mechanism of the create gold nanostars. And we think that gold nanostars were created after 15 minutes, because first we obtain a core which have a very similar shape to these nanoparticles, which we obtain after 15 minutes. So we think that the higher concentration of the reducer is responsible for the increase of the number of initial nucleation sites and the increase of the synthesis reaction speed. So we have too short time to react CTAB and the silver nitrate molecules. So we didn't have blocked the growth of the nanoparticles in 110 direction. Therefore, we obtain a dendrimer structure, and we obtain gold nanoparticles which have a star shape. So these nanoparticles we wanted to use in photothermal anti-cancer therapy. Therefore, we had to know something about the optical properties of these nanoparticles. And as you can see, along with the extinction of the synthesis time, the SPR peak shift towards larger electromagnetic wavelengths from 525 nanometers for spherical nanoparticles to around 800 nanometers for bone-like shaped nanoparticles. When we change the synthesis temperature, the UV spectra for these nanoparticles show that along with the extinction of the synthesis temperature, the SPR peaks have a wide range with a tendency to shift towards longer electromagnetic wavelengths. And for the gold nanostars, we obtain UV spectra which show that increase of the reducer concentration caused shift of the SPR peaks to the higher wavelengths. And moreover, for gold nanostars, we obtain very nice values of the absorbance. So from this data, we noted that the porous structure are responsible for the wide range of light absorption at wavelengths between 500 and 900 nanometers. And if we want to have the high value of the absorbance, we should have nanoparticles with high active surface. Therefore, we wanted to connect these two properties, morphological properties of these nanoparticles. And we obtain gold nanodahlias, which have a porous core and which have a large number of the arms. These nanoparticles are crystalline and they have a size around 70 nanometers. And as you can see, they have the SPR peak of these nanoparticles have a wide range between 500 and 800 nanometers. So next, we measured the temperature changes in the gold nanodahlias and gold nanostars and other nanoparticle solutions. When we irradiated this solution by 3 different wavelengths, 405 nanometers, 650 nanometers, and 808 nanometers. And as you can see, the highest temperature increase we observed in the solution irradiated by lasers 650 nanometers. And from this data, we calculate the value of the photothermal convection efficiency. And the highest value of this parameter we obtain also for 650 nanometer wavelength. So as I said, we wanted to use these nanoparticles in anti-cancer, photothermal anti-cancer therapy. Therefore, we added our nanoparticles to the culture cells, and next we irradiated these cells by lasers with 3 different wavelengths, and we obtained very nice results. And in the case of gold nanoparticles, which we obtain when we change the synthesis time, the highest cell mortality after irradiated by laser we obtain for the bone-like shaped nanoparticles. In the case of porous nanoparticles, the highest mortality of the cancer cells we obtain for the nanoparticles which have the smallest size, and the pores in these nanoparticles have the largest size. For gold nanostars, we obtain the highest mortality of cancer cells for gold nanostars with the longest size of the star arms. And for our gold nanodahlias, we also obtain very nice results mortality of the cancer cells after irradiated by lasers. So next, we wanted to know something about the dynamics of the accumulation of gold nanoparticles with different shape. And for this purpose, we used the holotomographic microscope, NanoLife 3D, which have very nice 200 nanometers resolution. And what is very important, we can image the cells in the physiological conditions without any bleaching and phototoxicity effect. Therefore, we can make experiments from 1 hour to even 1 week. And using this microscope, we can obtain the global information in what happens in our cells population. And we can also cut some fragments of our global population, and we can find information about what happened in one site, in one place of our cell culture. So in this experiment, we used 3 different shapes of gold nanoparticles: spherical, rod shape, and star shape nanoparticles. So, and as you can see, after 1 minute after added the gold nanoparticles, we didn't observe any morphological changes. However, after 25 minutes, we observed first morphological changes in the cells cultured with the gold nanostars. We observed the changes in the membrane, and we observed also create first apoptotic bodies. For rod-like shape nanoparticles, we observed first membrane change after 1 hour, 1.5 hours. And this time was a critical time for the cells culture with the gold nanostars, where we observed that our cells death. And for spherical nanoparticles, we observed first morphology changes after 3 hours, but this time was critical also for the rod-like shape, also for the cells cultured with the rod-shape nanoparticles. And after 48 hours, we obtained information that our cells were dead. So next, we wanted to create some nanosystem which we can use in a combined therapy. So we synthesized the gold nanoparticles which have a peanut shape, and the SPR peak of these nanoparticles is around 775 nanometers. So these nanoparticles we can also use in photothermal anti-cancer therapy. Moreover, these nanoparticles have a positively charged in the anterior range of the pH. And next, these nanoparticles we functionalized, and on the surface of these nanoparticles we immobilized anti-cancer drugs. And next, we measured the Raman spectra, and we made some colorimetric measurements because we wanted to know something about the successful of the functionalization process of these nanoparticles, and we wanted to know something about the temperature, the critical temperature in which our nanosystem is stable. And colorimetric measurements show that created nanosystem is stable up to a temperature of 110 Celsius degrees. And these nanoparticles we added to the glioblastoma culture cells. And next, we irradiated these cells by X-ray. And the highest cell mortality was observed for cell lines subjected to our nanosystem combined with radiotherapy, from 20 to 55%. followed by single anti-cancer drug, where we obtain the mortality of the cells between 1 to 15%, and same X-ray irradiation of our cells caused the mortality of our cells about 1%. So at the end, I wanted to show you some results for gold platinum complex, which we used in proton anti-cancer therapy. So we obtain gold platinum nanoparticles, which are crystalline and which have a size around 66 nanometers. And these nanoparticles we added to the control cells and to 3 different colon cancer cells lines. And first we wanted to know about the non-toxic concentration of our gold platinum nanocomplex. And as you can see, the non-toxic concentration of our nanoparticles depends on the cells line. Next, this non-toxic concentration of our gold platinum complex we added to the cells, and we irradiated these cells by a proton beam, and we obtained very nice results in the mortality of our cancer cells from 60% for control cells line to 41% for colon cancer cells line. So we can say that proton beam therapy which is assisted with our gold platinum complex are more effective than proton radiotherapy without the presence of our nanoparticles. So let me conclude. The value of the gold nanoparticles conversion efficiency increased with the extinction of the synthesis time, the decrease in the pore size with increase in their number, and the increase in the length of the nanostorm arms. And the position of the SPR peak for gold nanoparticles shift towards the larger wavelengths along with the increase in the synthesis time and the length of the arms of nanostars. Longer synthesis time, higher temperature, and higher concentration of the reducer cause greater crystallinity of the obtained gold nanoparticles, which can be used in photothermal anti-cancer therapy. The dynamics of the accumulation of gold nanoparticles depends on the shape of these nanoparticles, and combined anti-cancer therapy is more effective than single therapy, and our gold platinum complex we can use in proton beam irradiation of human cancer. And at the end, I would like to thank all of my group and you for your kind attention. So thank you very much.
Yes. Any questions? Any questions to Dr. Joanna? If you have any questions, just you can text us through chat box. We will be asking behalf of you. Any questions to Dr. Joanna? Yes. Thank you very much, madam. Thank you very much for speaking up in this meeting and providing a unique perspective. Thanks for sharing your tips with us. Looking forward to meet you again next time as a physical event. Yes. Now we ask Dr. Geoffrey from Mitchell, Central of Rapid and Sustainable Product Development, Polytechnic of Alferia from Portugal, to start the presentation.
Right, thank you. Good morning to you all. It's a great pleasure to talk to you this morning about recent work on the dilemma of nanoparticles in polymers. And what I mean by this, I hope will unfold as we go along. So this work is performed at the Centre for Rapid and Sustainable Product Development, which is a centre of excellence in the field of additive manufacturing, and in which this presentation has some relationship, and was supported by national funds from the Science and Technology Foundation of Portugal. So additive manufacturing is a process of taking a digital definition and turning it into an object without the use of specialized tooling or molds, and is a methodology in which many people think will be how all things are made in the future. So I want to start with something topical, which is in the COVID pandemic. We know that face masks and other personal protective equipment is the front line. Now, with a variety of people in different European countries, we've been working on developing a new approach to face mask, which is summarized in the paper shown in the citation at the bottom. Now, one of the strands which we're very conscious of in terms of face masks is that the number of face masks required by public use, not by medical profession, is of the order of 130 billion pieces. And so this produces a huge amount of waste each week because these are disposable face masks. And so this consortium, of which I'm part, has published a visionary roadmap for the development of personalized reusable face masks, which has smart nano-assisted destruction of pathogens. And so this follows on very well from the last presentation. And so briefly, this face mask uses electrospun fibers as the basic filtration, but one of the layers of the electrospun fibers contains gold nanorods, which, because of the photothermal effects we've just heard about, can be used to generate a heating effect, which is sufficient to kill the virus. And so hence the mask moves from being capturing viruses and then needing to be disposed, because otherwise you'll be exposed to the virus, to being one in which the virus is killed and therefore the mask can be reused. Now, the success of this approach depends upon the use of nanoparticles, because it makes it easy to have high efficiency photothermal effects to kill the pathogens. And of course, this makes a very highly efficient face mask, but it doesn't think about how we might recycle or reuse these materials. And that's the central part of what I'm going to talk about. So if we recycle multi-component objects, such as a face mask, which is made from electrospun fibers and nanoparticles and some other materials, then for reuse, we need to be able to separate these out, and the various technologies to do this, which depend upon density, magnetic properties, some in the case of visual identification. And many of these separation processes become much more challenging with the use of nanoparticles. Now, another large area of application of nanoparticles in polymers is food packaging. And we're familiar with food packaging, and the packaging provides a barrier to prevent maybe a positive interior atmosphere reducing by leaking to the external atmosphere, or for the external atmosphere in the form of oxygen making its way into the interior of the system. Of course, the barrier prevents the ingress of bacteria, prevents damage to food, and in general, most food packaging is transparent, so the consumer can see what's on the inside. Now, one way to achieve a more efficient food packaging system is to include in the barrier some nanoparticles, which doesn't come up in this picture, but I'll explain what this purpose is. So if we want to reduce the gas flow through the polymer film, then we need to have low permeability components. So the polymer itself is quite permeable, and so we need to include low permeability with the material. Now, if this material is organized in the form of thin layers normal to the gas flow, then it requires the gas flow to have a tortuous path, which moves around, has to translate sideways in order to move forward, and so it makes the pathway much longer. Of course, in a polymer film, one of the challenges is how to organize such layers of low permeability. Now, one way to do this, as has been proposed in the literature, is to use self-assembling films. So that, for example, tri-block copolymers are well established as an industrial material, and these can form alternating layers of glassy and rubbery layers. So the rubbery will have a high permeability, as shown in the graph in the inset, and the glass will have a much lower value. And if we arrange these in layers, then the permeability is the sum of the resistance of each of these layers, as shown here. Now, we can achieve the same if we were to include mineral flakes, such as mica or other things. Flakes are obviously much more efficient, as shown in the graph, of reducing the permeability using low fractions, whereas to achieve a similar reduction, we need to add very high proportions of spheres or cylinders. And so there's two aspects to including these particles. They need to have a high aspect ratio. So in this case, the vermiculite has an aspect ratio of 30, and they have to be organized so that the plane of the flake is parallel to the surface of the film, so that the transport is impeded most efficiently. And so if we do this, then we can reduce the permeability by a factor of 6.3. Now, of course, we could equally use nanoparticles, and this is just showing the effect of the nanoparticles on the permeability and generating a tortuous path, which means the diffusion path of the gas molecules is very much longer, so it takes a longer time, so the rate of diffusion through the system is much lower. And with nanoparticles, then these can be safe. Montemurrolite, which is derived from clay, is already used in pharmaceutical products, and it's possible to use self-assembling nanofibrils, more about that later, which are approved for food use. Now, the nanoparticles can also have other properties. They can be antibacterial, they can lead to in changing in the electrical conductivity, they can change the mechanical properties, and they can modify the polymer matrix by acting as a nucleant for the formation of crystals and directing the crystallization. Now, there are different shapes of nanoparticles. So we have carbon nanotubes, halloysite, which is a particle similar to a nanotube but formed from mineral. We can have self-assembling fibrils. We can have plate-like, graphene and montemurrolite. We can have spherical particles. Now, each of these different particles has a different impact upon the barrier properties, and all this is reasonably well understood from a theoretical point of view. And so, in the simplest way, it depends upon the volume fraction, the aspect ratio of the particles, and the orientation of those particles. All three of those factors are important. Theory is well developed, particularly for dilute and semi-dilute systems. When you go to higher concentrations, it becomes more dependent on the particular systems that are being using. So in the semi-dilute regime, this tortuosity becomes important. So this is just explaining the reason for the tortuosity. So in order to move forward, the molecule has to undergo lateral diffusion. And so it's relatively easy to work out the impact upon the diffusivity. And as shown, this depends upon the reciprocal of the square of the volume fraction and the aspect ratio. So nanoparticles with a high aspect ratio would be very efficient in this process. So this is just summarizing this. So the enhancement in the diffusivity or the diminution, the diffusivity depends on the volume fraction of the particles and the aspect ratio of that particle. And this is taken the fact that that particle is aligned parallel to the surface of the film. Of course, these will have, as I mentioned, other impacts on the system. Now, this is an alternative way of achieving this, the same thing, which is to use a stack of multi-layered films, which can be generated using a technique that's been developed at Case Western University in the work of Wang, etc. And here there's a stack of polystyrene and polyethylene oxide layered materials. Now, the polyethylene oxide will have a high diffusivity, whereas the polystyrene, being glassy, will be very much lower. And you can see that these multi-layer stacks can have a large impact upon the flux, in other words, the amount of gas passing through. And so it's possible to produce a very efficient food packaging material. But although this is a very effective solution, it's then very challenging to think how the materials that are used in these very nanoscale films, could be separated during recycling. If we want to reuse the materials, we need to sort them into the component parts so we can rebuild a structure that has the similar properties. Now, there's a huge consumer interest in food packaging because everybody thinks they're an expert in food packaging, and there often appears to be alternatives. But really the key to thinking about food packaging is the end of product life solution. So what happens to the packaging after it's served its purpose? Does it go as do 2/3 of the material go into landfill, or is there a way of recycling the material? And so recycling is not just one line. It could be that it's recycled to extract the energy, so it's incinerated. There are methodologies that people are developing at the moment to break polymers down into the monomers so that the material can be repolymerized. But there's a variety of ways in between. And in order to do this, in terms of the material needs to be separated. And so if we work with a nanocomposite, we need a separation method for the matrix polymer and the nanoparticles in order to maintain the composition of the film. If we just recycle the whole lot, the composition of the film will change as with the order of the recycling. So this is the sort of crux of the problem. If we are to use nanoparticles, these can deliver properties which may not be possible to deliver in other ways. So killing the virus in the mask is an example, providing efficient barrier properties to prolong the life of the food. And if we can make the whole life of the product more straightforward, if we design the materials and the product for recycling, so not just to achieve this wonderful barrier properties, but also to think how this can be how it can be recycled. So if we design the material and the product to be recycled, it will reduce the demands on the recycling and separation stages at the end of the product life. So for example, a very simple example would be the use of magnetic particles could greatly simplify the separations of the particles from the polymer. And there will be other considerations which will be critical. And so we should also explore the proper design of the products without recycling. Now, since we're talking about polymers, many of the polymers used for food packaging are semi-crystalline polymers, and these actually contain nanoplatelets in the form of chain-folded crystals, which may have a thickness of 10, 20 nanometers, lateral dimensions of 1 micrometer, and hence has an aspect ratio of 50 to 100. And it's possible to organize these lamellar crystals to have a very common alignment, as shown in the electron micrograph on the right. This shows a differentially etched surface of a polyethylene blend prepared with a very high level of common orientation of the chain-folded lamella. In this case, the chain-folded lamella are arranged so that they're normal to the screen that you're looking at. So they're aligned. So in this particular case, if the film thickness was in the plane shown there, this wouldn't be very effective because it wouldn't provide a high level of tortuosity to impede gas diffusion. But this perhaps provides us with a way which we can think about how to do this. Now, one way which we've been exploring at CDRSP is the use of dibenzylene sorbitol, which is a material which is approved for food use by the Food and Drug Agency. And this forms extended nanoparticles in polymer matrices, as shown in using the X-ray diffraction pattern data. And this can be used to control the chain-folded lamellar morphology. So if we organize these extended nanoparticles, then these can act to template the crystallization of the thin lamellar particles, the thin lamellar crystals, and in that way. And indeed we've demonstrated, and this work was published recently, in which it's possible to use these particles to arrange for the chain-folded lamella to be in a similar arrangement as we just saw, or by controlling the composition of the material for it to be arranged so that the planes of the lamellar crystals lie perpendicular to the plane of the film, and therefore do indeed provide a tortuous pathway for gas diffusing in a horizontal direction through the film thickness. So there's an alternative method of doing it. So to summarize, nanoparticles can greatly add to the properties of a wide range of polymer products. Examples are filtration, face masks, or in other filtration processes, electrical conductivity, mechanical properties, etc. And although the inclusion of nanoparticles can deliver high performance, the product must be designed for the whole life cycle, including the end of product life and recycling. Appropriate choice of nanoparticles may greatly ease the process of separation during recycling. In the case of polymer packaging, the addition of nanoplatelets can lead to enhanced barrier properties, for example, using nanoclay. But by using the full capability of polymer processing coupled with the use of self-assembling nanoparticles, which then have different properties and can be unassembled, it's possible to gain similar advantages. Thank you very much.
Any questions? Any questions to Dr. You are free. Yes, thank you very much, sir. Thank you very much for speaking up in this meeting and
Right.
providing a perspective.
Right,
Thanks.
thank you.
Yes, thank you. Thank you for sharing your tips with us. Looking
Yes.
forward to meet you again next time.
Yes. Thank you.
Thank you.
Bye-bye.
Thank you. Now we ask Dr. Vijay Chelivendra, from Professor in Mechanical Engineering of Dharmati from USA, to join the event and start presentation.
I think I was muted. Can you see the presentation?
Yes, sir, it's fine.
Okay, can you hear me properly?
Yes, sir.
Okay, thank you. So I'm Vijay Chelivendra. I'm the professor in Mechanical Engineering Department from UMass Dartmouth. I thank the organizers for giving me this opportunity to give a keynote lecture on carbon nanotubes embedded natural fiber composite materials for damage monitoring. We have been working on this topic for the last, I can say, 11 years on damage sensing. Recently, we got a couple of grants from National Science Foundation to understand how carbon nanotubes can be exploited to understand the damage in these natural fiber composites. So if you talk about the motivation of the natural fiber composites, traditionally people use glass, carbon, Kevlar, fiber-based composites in the composite structures, used in even defense as well as civil applications like automobile industry. However, there have been a lot of interest to use natural fibers because of natural resource availability, biodegradability, sustainability. People have been using it inside the cars where there are no external loads applied on these on these situations. For example, as you see in this picture, there are a lot of parts were made which were actually used in this Mercedes-Benz car, but they're actually use them inside the car where there is no external load. So the reason why people have not been using by then was these natural fibers are not very strong compared to synthetic fibers. So there is a need for improvement of improving the strength of these fibers, improving the toughness of these fibers in the applications so that they can be used outside the car where the loads are applied. For example, as you can see here, there is a car door and also the bumper and on this hood plate. All these things can be made right now with natural fiber composites, where these are things actually recently has been used in Tesla cars, where they have been using it for external loading conditions. And also you see in applications where they also use it in the wind turbine blades. And most importantly, you can see here, there is a footbridge. This bridge is made of natural fiber composites, which is made of flax fibers, where it can withstand the mechanical loads. So that's a great news actually, because we want these natural fiber composites to be used under structural load-bearing applications. Then we should be able to replace them with traditional composites where they can be a really better candidate in most of the recyclable applications. And you can also see geotextiles were made of natural fibers extensively. It has been there for a while. Now, in this study, we wanted to really make these natural fiber composites much more attractive. That's the motivation why we wanted to do this study. So we want to make them multifunctional. Multifunctional means we wanted to improve the mechanical properties, fracture properties, at the same time, whether they can be used to sense the damage in the composite. So that's the basic application of basic motivation for behind this study. And then if you look into literature these days, structural health monitoring is one of the major aspect where people are looking for, where they wanted to monitor the structures so that they want to avoid catastrophic failure of the structures, maybe do periodic maintenance, make sure that the structures are safe under mechanical loads. And as the natural fiber speaks about itself, that can actually reduce the greenhouse gas reduction and also have a sustainable global economy with these natural fibers. Now, coming to fabrication, as everybody know, these natural fibers are cellulose-based fibers. Cellulose-based fibers absorb water a lot. So we need to make these fibers, first thing we should do is we have to make them hydrophobic. So then only you can use them in real life applications for long service life. Otherwise, they degrade very quickly, and then they break very fast, so that you cannot have a long life. Hence, the first thing we're supposed to do is to do some treatments. So in this study, we use jute fabric. Jute is kind of very cheap to buy. So actually, we did not even buy. We got free samples from a local industry to do this study. Jute is very well known in the literature, has been studied a lot. So we found that is going to be an ideal candidate for us to pursue the research. So we use the jute fiber, where the jute fiber has to subjected to alkali treatment and then saline treatment. So I'm going to talk about those two treatments first before I get into the rest of these blocks. Okay, now alkali treatment. Now, in case of alkali treatment, we use 5% aqueous NaOH solution. So, and then we treated using this solution all the jute fabrics, I can say jute yarn. Then we use them to make the composite. So before we make the composite, we did FTIR spectra, as you can see in this image, where the absorbance values drop due to alkali treatment at the peaks of 1244 centimeters per second, and 1745. So at these two locations, as you can see, there's a drop in the peaks. This is the alkali treatment. Okay, so because of alkali treatment, the drop is actually can be noticed. So these two peaks represents ester groups and carboxylic acid. Okay, so these are the constituents of hemicellulose. See, when you take a jute yarn, it consists of three things: cellulose, hemicellulose, and lignin. So cellulose is what we want to hold. We don't need hemicellulose. Hemicellulose is like a wax-like product that holds these fibers together. So if you can get rid of this wax-like product, then basically you can open up the jute fiber. So hence, we want to make sure we just want to get rid of hemicellulose from this jute fiber. So that's the purpose of doing alkali treatment. Now you can see, the treatment was very successful because these drops signifies that we removed these groups. These groups belongs to this hemicellulose. So once that treatment is done, then we went to saline treatment, where we use APTMS saline, which was brought from Sigma Aldrich. This was used, and then once you apply this treatment, as you can see, this treatment actually represents, there's a peak here, which is 1084. This peak represents SiOC bonding, means this treatment really created these bonds within the jute fiber. So that gives you impression that this saline treatment was really successful, where it really bonded well with the cellulose chains rather than simply just adhering to that. Hence, we've proved the efficacy of the APTMS treatment on these jute fibers. Now, how do you verify that the treatment was successful? Now, you want to verify that means we put this fiber in a bath, small cup where you have water here, and these fibers, we wanted to see how much water it's going to raise, Viking distance, we call Viking distance, how much it's going to go up as time passes. Now, as you can see, the raw jute, which is the blue curve here, where the raw jute actually gets the water content going into the fiber, keeps on going. It's going to get saturated after a while, after 100 hours, sometime like that. Now, if you take alkali treatment jute, where you can see the red curve, where it's actually more than the raw jute, which is very interesting, right? So why it is so? Because as I was telling you previously, once you do alkali treatment, you remove the hemicellulose. The hemicellulose removal opens up the jute yarn. So when it opens up the jute yarn, water can penetrate, easily water can penetrate. Hence, you see a better rate of increase of water content compared to raw jute. Now, if you look at the APTMS treated jute fiber, as you can see, there is no water content, pretty much, zero water content. So this gives you a strong confidence that there is no water in the fiber, so that this treatment was very successful, and we have a hydrophobic fiber now. So hydrophobic fiber is what we want to achieve to use it in the composite fabrication. So I think we are successful making these fibers hydrophobic. Now let's get into rest of the process where we use carbon nanotubes. So everybody may be aware of these carbon nanotubes. Maybe I don't need to go through a lot about it, but one property which was very interesting to us was electrical conductivity, because we want to make the composites slightly conductive. We don't want to make them super conductive. We want to make them conductive enough so that we should be able to detect the damage inside the composite by using piezoresistive approach. Now, as you know, carbon nanotubes have a current carrying capacity almost 1,000 times more than copper wire, which is highly conductive, and they have a very high stiffness. We are not really worried about stiffness because stiffness is not our concern. The important thing we are interested in is actually the aspect ratio. So the aspect ratio comes from the length of the carbon nanotubes. See, as you can see, the length is around 2 to 20 microns when compared to diameter. So the aspect ratio gives you very good network. If you look at the spaghettis, as you can see in this picture, you see a very good mat-like network when they are spread in the epoxy matrix. And we employed in this study multi-wall carbon nanotubes because they're cheaper, so they can actually provide a good network as well. Now, coming to fabrication. Now, in this study, we use the matrix, which is thermoset epoxy, which is the two-part epoxy. So here, what we did was we took the part A, which is the resin. We required amount of part A, and then we took the weight of the required amount of carbon nanotubes. We did hand mixing here, and then we went to combination of shear mixing and ultrasonication. The shear mixing is a global mixing. It's not really is going to do a mixing at nanoscale, where we don't really separate the carbon nanotubes at the scale of nanometers. So shear mixing does kind of a global macroscopic mixing, but it is very effective when it comes to nanoparticles. And ultrasonication is going to be really generating a separation between carbon nanotubes. So we did this one as a combination, not doing separately. In the past we did separately, but we came to know that by doing together we should be able to have an effective dispersion of the carbon nanotubes. The key here is you must disperse these carbon nanotubes really well. Otherwise, you cannot really successfully make a nanocomposite. So then, once you do this for 1 hour, and we put this one in vacuum chamber where we want to make sure, we take care of take away all the air bubbles, air pockets during the process of mixing. And then we added a part B, which is the hardener of the epoxy resin to make it, to start the solidification process, gelling process. But we got to do again one more shear mixing so that this part B is well mixed with carbon nanotubes, and then do one more time vacuum infusion for maybe a short period of time, because once we add the part B, it's going to start gelling, so that we have only 2 hours of part life before we infuse the epoxy into composite. So we should be really quick to do this one in between these processes. Good. So we did some study way back in 2000, maybe 2010 or 12, where we wanted to see how much sonication is required. Basically, people do sonication for a long time. If you do sonication for a long time, what happens is you're going to break the carbon nanotubes. Break the carbon nanotubes, the resistance of the composite is going to go high. So this is actually, CNTs in epoxy matrix. We just did the simple study to understand how long sonication is better. Now it seems like 1 hour is good enough to get reasonable amount of dispersion, so that we kind of went with 1 hour. Now how much amount of carbon nanotubes is good? Now people put a lot of carbon nanotubes. If you put more carbon nanotubes, you have more agglomeration of the composite. So there's no point in putting a lot. So as you can see, it reaches a plateau here in this picture. By increasing amount by 0.2, 0.5, we generate basically, same kind of resistance what you are going to get. So we, in our study, we use 0.1%, which is kind of, sometimes we use 0.025%. I'm going to talk about it in a few minutes, where we should be able to generate, a reasonable amount of resistance. We don't want actually very low resistance. Okay, we want resistance somewhere in this zone where, you should be able to detect the damage in the system successfully by using, a system like this. Good. Now, coming back to this diagram, so we did the dispersion of carbon nanotubes. We talked about the jute treatment. Now we actually use two different orientations of jute. One is unidirectional; all the fibers are actually aligned in one direction. Other one is 0-90, which is a cross ply. 0-90, you can see my fingers, 0-90 like this cross ply. Now once we have this alignment, and then we went to wet flocking process. This is a UMass Dartmouth patented technology where we did actually reinforce short carbon fibers into the jute fabric. So how did we do that? We have two plates, conductive plates here. One is the top plate, there is the bottom plate. These two plates are connected with a differential potential, voltage potential of 100 to 60 to 100 kilovolts. And then there is a reinforced fabric, the reinforcement, which is actually a fabric, is attached here on the top surface. We put a small layer of epoxy with CNTs. Actually, this should be epoxy plus CNT. Yes, tiny layer of this mix is actually kind of spread on top of the fabric, and then we have on the bottom we have short carbon fibers. These carbon fibers are two kinds. We use 150 micron length and 350 micron length. So these are the two kinds of carbon fibers. We use them in this study where they were actually placed on the bottom plate. Now, once we apply a voltage of 60 to 100 kilovolts, these fibers actually just jumps up. They just go straight and want to stick to the laminate. So when they stick to the laminate, you generate some kind of reinforcement here normal to the fabric. That's what you see in this picture. This is the fabric, as you can see. This is the fabric here. On the fabric, you have these short fibers, which are actually going up. Okay, so they will actually give you a good network, conductive network within the composite because they're carbon. Then moreover, basically, they also provide you very good fracture resistance. When the crack is propagating, they kind of stop the crack, bridge the crack, so that you get very high fracture toughness. So that's why this technology has been there, at UMass Dartmouth. We're successfully applying it in different situations and making different types of materials for the last 20 years. Now, so coming to making composite. So what we do here is we kind of laminate, stack these fabrics one after other, just kind of hold them together, and then we infuse the epoxy with the CNT matrix, CNT, through this inlet. We're going to use some kind of vacuum here to let this one go through, and then it's going to actually penetrate through the laminates, and it's going to have a very good dispersion of the matrix, and it's going to come out. This is a standard process. I'm not going to go through a lot of details about this vacuum infusion. A standard process people apply to make composites. Now, coming to electrical measurement, this is very important because people have been measuring electrical resistance in the past, but they don't really put some attention to the instrumentation. Instrumentation is very important because when you are measuring these materials which are having high resistance, you got to be really careful with what kind of current source you use, what kind of voltage measurements you make. So hence we paid a lot of attention to that in our first proposal to National Science Foundation, where we want to make sure we have right instrumentation so that these measurements are accurate, publishable. Now, as you can see, we have a current source. I think this is actually a current source here. This current source sends a constant current through outer probes. We use a 4-point probe method, ring probes, where the probe is actually, the silver paint is attached to the sample, a composite sample here. Assume this is a composite sample here. The silver paint is attached actually as a ring around the sample. So when you send the constant current, it's going to pass through the outer probes. Technically, it's going to pass through the whole this area, gauge length area. Now we measure the voltage using multimeters, electrometers. See, the electrometers are so important because they have a high impedance. Because of the high impedance, they don't let the current to leak. They don't let the current to leak through this instrumentation. So that you always maintain a constant current. The reason why you have to maintain constant current, I'm going to use a simple law, Ohm's law here, V equals to IR, where I is supposed to be constant. If I is not constant throughout the experiment, then the measurements are wrong. So that's why, I think, that's why I'm talking about instrumentation. Instrumentation is supposed to be really, really good when you're doing experiments like this. Now, then you measure the voltage here, voltage, voltage difference between voltage here using electrometers. And then, you take a difference between these two measurements of electrometers, you get the a voltage difference between those two inner probes, which is going to come from the multimeter. So these, look at the instrumentation resolution here, okay? Very, very small resolution I'm talking about. You have microvolts resolution. And here you have nanoamps resolution. So such a high resolution instrumentation is required when you are doing experiments like this. Now, once you have the resistance value measured from using the Ohm's law, because I measure the voltage difference between these two probes, use the current, what you get from here, what you supply, and then you measure the resistance value as you are applying a mechanical load. And when you are, for example, I'm going to pull this one, in the vertical direction, I should be able to measure the change in resistance by due to the damage inside the composite, for a given applied load. Now I use the formula here, which is R bar over R bar minus RO over RO, where RO is the initial resistance of the material, where you can measure the resistance, change in resistance, from this simple formula. Now, this is a cloudy result. I'm going to go through these results pretty slow. As you can see here, we have different variables, which is carbon nanotubes weight percentage, which is 0.1% and 0.025%. Very, very small amount of carbon nanotubes. The reason why we are able to put small amount, because we have carbon fiber. When you have carbon fiber, we have a luxury of generating better conducting network. So you don't need to put a lot of carbon nanotubes, which are very expensive. Now, as you can see, there is a slight difference, between 0.1 and 0.025. With 0.025, you see some increase, when you compare to this curve. Look at this curve, okay, and kind of, a little bit high. But I really don't, worry much about, in this increase, because you see pretty much, you see similar curves, most of the case. So 0.025% is also good enough to make composites. You don't need to go for even 0.1%. That's the message I want to give you from this CNT amount. Now we did actually two different laminates, 000, 090, 090, which is a cross-ply composite, where you can see a slight decrease in the resistance. When you can compare this curve with this data with this data, there's a slight decrease in resistance. That's because I'm going to show you a small picture here, a cartoon here, where these are all unidirectional, where they're going in one direction. As you can see, these are 090, these are 0, these are 90. Then the reason why 090 generates a better network is because there's a gaps here. Look at the gaps here between these gaps. Okay, so these gaps are actually very good gaps, where the carbon fibers can go and penetrate. And these dots are carbon nanotubes, by the way, in this picture. So they make a good connection with the neighboring carbon nanotubes, so that the network is going to be very, very good. You can generate a three-dimensional conductive network. The three-dimensional conductive network is actually much better in 090 condition compared to 000 condition. So go back to this picture again. Now we have two different carbon fiber lengths, 150 and 350. Now look at the 150 and 350. 150, is very high. Let's pick some, fiber density here, which is 500 fiber density. But 350 fiber density, the value is here, several orders of magnitude lower with 350. The reason why is basically, I want to go back and look at the schematic here again, because 150 fibers, they penetrate, but they don't penetrate enough to generate a good network. However, 350 are longer fibers. They can penetrate into the laminates. Hence, they can actually give you better network. And maybe I will show you one more picture here, where I'm talking about the gaps here. In the gaps, 350 fibers can actually go inside, go between these laminates, these fibers, and generate a better network compared to 150. Hence, we can clearly see 350 is much better than 150. Now, coming to flog density. Flog density is basically amount of fibers you put them on the laminates. So if you put 500 fibers per millimeter square and 1000 fibers per millimeter square, you don't see a big decrease in resistance. Okay. However, as soon as you put 500 more, as you see 1500, 2000 fiber densities, even at 150 micron length carbon fibers, you see a deep, a sudden decrease in actually resistance. This is because 1500, 2000 are optimum amount of carbon fibers you're supposed to have if you have 150 fiber, 150 long carbon fibers to generate a good network. Now, coming to 350, you want to put 500 fibers per millimeter square, you generate the network, good network comparable to 150 with 2000. 350 is very, very rich network compared to 150, even with 500. As you increase the amount of carbon fibers, you don't see big decrease in resistance, but you still see a decrease, but the decrease is not as drastic as 150. So this really gave us a very good understanding of what is the optimum amount of carbon nanotubes and what's the optimum amount of carbon fibers and the length of the carbon fibers you should be able to put in the composite to generate the required amount of resistivity you want to generate in the composite, so that you have a better design choice here to develop these composites. Good. So next one I want to talk about is shear loading. What happens to this change in resistance of these materials when I apply a shear load? So because why shear loading? As you can see in this picture, technically composites undergo shear delamination. As you can see, a lot of delamination happens between the composites under shear loading conditions. So shear loading, interlaminar shear is very important failure mechanism in these composites. Hence, it's very important that we should understand and study these composites under these shear. Now, to study this one, what we did was we employed ASTM standard, which is ASTM D3846, where we have a composite, where we have, this is a composite sheet. This is the side view, and this is the top view. If you look at the side view, we made two notches, a small notch here, there's a small notch there. These two notches actually generates a shear loading. When you pull this sample, when you pull it here under tensile loading conditions, then this is the zone where you see shear loading. This is the zone where you have a shear deformation. Okay, so that's why I know this is a simple specimen configuration where you should be able to generate the shear conditions between these two notches. And also we have a 4-point probe here. These are current probes, and these are voltage probes. Okay, so as I discussed with you previously, using the same instrumentation, we should be able to go and measure the change in resistance under shear loading conditions. Now, so these are the interlaminar shear strength. The interlaminar shear strength of the composite, as you can see here, this is actually a cross-ply composite. This is a unidirectional composite without any carbon fibers. These are without any carbon fibers. So if you put the carbon fibers, we notice an increase in the interlaminar shear strength. So this is what I'm talking about, multifunctionality. So we want to make sure these carbon fibers not only helps you to detect the damage, but also improves the shear strength so that they do multifunction. So here the shear strength reaches a maximum value. It's almost like, this is values around 40, I can say 40, and this value is around, 25. There is a significant increase of 15 megapascal of increase of, shear strength by adding the carbon fibers for this orientation. So this is a good news when you want to use them as a multifunctional material. Around 50% increase in the resistance. Now, coming to electrical response, as you can see in this picture, so I'm showing you only for one case here where the carbon fibers are of length of 350 microns and with a density of 1000 fibers per millimeter square, and the orientation is 090-090 orientation. So for this orientation, I'm picking actually composites of 0.025% carbon nanotubes and 0.1% carbon nanotubes. So as you see in this picture, this is the shear stress, the vertical axis is shear stress, the horizontal axis is shear strain, and this is the percentage change in resistance. Now, there is a zone, we divided this electrical response. The red curve is electrical response, the blue curve is stress strain diagram, shear stress, shear strain diagram. So as you can see, the red curve, we divided this into two different, I think the red curve is stress strain diagram, I'm sorry for that. The blue curve is, electrical response, okay? So sorry for the confusion. Now here, we divided it into 3 zones. The zone 1 is actually, there is no change in resistance. Here also, there is no change in resistance in this zone. The reason why there is no change in resistance as soon as you put the mechanical load, because we have a small cartoon here I want to show you. Here, when you do the shear loading actually is a horizontal loading like this. So when you have a small amount of carbon nanotubes, what happens is when you apply a shear loading, the carbon nanotubes generates a network by shifting from previous carbon nanotubes to new carbon nanotube. They have a new network is generated between these carbon nanotubes when they are shearing. That's why you don't see any change in resistance. So that's much more predominant when you talk about 0.1%, because you have a lot of carbon nanotubes and they can generate the new networks with the neighboring carbon nanotubes. Hence, you don't see change in resistance as you can see in this pair. Okay, in case of zone 1. when you go to zone 2, you start seeing change in resistance because you start breaking the network, and there is a micro cracks formation, and interlaminar delamination. That's going to increase the resistance. The interesting thing here is, as you can see here, the zone 2 maximum resistance, at the end of the zone 2 is basically around 15%. However, here the percentage is only 5%. The reason is because at 0.1%, carbon nanotubes in amount, you have a really good network. So this network actually, even though you are under shear loading conditions, you are not really, even though you are breaking the network, that because of the rich network, you generate again new contacts. That's the reason why you have a small amount of change in resistance in case of 0.1% compared to 0.025%. However, when you reach this, when you start breaking the sample, when you reach the maximum stress, the values are pretty close, in both cases. But however, the network is so rich in 0.1% compared to 0.025%. Now, these are the curves I want to show you for different fiber densities, where we took the system of 0.1% weight fraction of carbon nanotubes. This is 090 orientation, again 350 microns carbon fiber length, and we have 4 different fiber densities. As you can see here, first one, 500 fibers per millimeter square, where the zone 1 is again same thing what we discussed a few minutes ago, but zone 2 is very different compared to other 3 cases, where the resistance is decreasing. There is a reason why that is going on, because at 500 fibers per millimeter square, you have very small amount of carbon fibers. Then the network is dominated by carbon nanotubes. So because of carbon nanotubes dominance, what happens is when you're applying the shear loading, they undergo Poisson's ratio. They undergo Poisson effect. The Poisson effect brings the carbon nanotubes together. So when they bring them together, you have a rich network. Then the resistance decreases as the load is applied. That's the scenario which we also observed in our composites without any carbon nanotubes, without any carbon fibers in our previous study. Now coming to 1000 fibers per millimeter square, where you see there's increase in resistance because you have carbon fibers are coming into picture, where delamination of carbon fibers and then decreasing the network would also play a role there, where you start seeing microcrack formation after a while. Then you start increasing resistance. Now the important point I want to make here is, look at the maximum resistance here, which is around 30%. It becomes 15% here, it becomes 10%. The reason why it happens because as you increase the amount of carbon fibers, you start having a good network. Then the good network actually would actually decrease the total amount of resistance, because as you are breaking the network, you start again forming the new contacts. That's why you see the decrease in resistance when the specimen is breaking. Now coming to fracture loading, which is a very, very important for us, for mechanical engineers, where things undergo fracture mechanics. Now we have a composite here, as you can see in this picture. When you pull the load, when you put a load here on the hinges, you generate the crack to propagate. Now what happens with the change in resistance when the crack is propagating? Now for that one, we use the DCB sample, which is a double cantilever beam sample, as you see in the previous picture. Now this is the sample dimensions. We put a current probe, voltage probe in a clever way, because there was no standard. We have to develop a novel methodology to generate this, to put these probes so that we should be able to measure the resistance properly. Now what we did was we sent the current through thickness. There is a current probe here, a loop probe. There is the same probe in the bottom too, and the current actually passes through from top to bottom. And we have these voltage probes that are attached. As you can see, look at follow my cursor. This is the voltage probe. Okay, actually it's going to go circumferentially above the crack and below the crack. Okay, below the crack there is one more voltage probe. So these voltage probes will measure the change in resistance when the current is applied from the top to bottom. Now, other important thing I want to talk about is look at the fracture toughness values. This is the composite without any carbon fibers. This gives a value around 1.5. Now, if I put carbon fibers, you can increase the toughness by 75%. Maximum value is going to be somewhere here. So again, I want to re-emphasize that we are targeting to make multifunctional composites. So that's why we want to improve the interlaminar fracture toughness, interlaminar shear strength. So those are the 2 things we achieved in this project. At the same time, we are able to measure the change in resistance under fracture loading as well, as I'm going to show you in the next slide. So why it is so? Why you are able to generate higher fracture toughness? As you can see in this picture, this is the SCM image where you have no carbon fibers. You see a smooth fracture surface. A smooth fracture surface indicates the crack can propagate, easily. That's the meaning of a smooth fracture surface. So, however, if you have a fibers there, these short fibers actually bridge the crack growth because you have a rough fracture surface. The rough fracture surface indicates the fracture toughness is very high. Okay, that's the difference between smooth and rough. So that's what you see also in the previous slide, that there is increase in fracture toughness as you increase as you have a carbon fibers in the composite. Now, coming to electrofracture response, here we have load as the vertical axis. The displacement is the horizontal axis. That's what you see here. There's a load is applied here, and you get the displacement. How much displacement you have in the crack here? You can see that one. That's the horizontal axis, and this is the percentage change in resistance. Now, as you can see, there is no much change in resistance before the crack initiation. This point belongs to crack initiation, by the way. Exactly, this is the point of crack initiation. At that point, crack initiates, means crack actually starts propagating. Now, at that location, you don't see big change in resistance. This is pretty much, pretty close to maybe 10%, 20%, not more than that. So, however, you start seeing the crack growth, increasing resistance as the crack is propagating. You see a steady increase in, a linear increase in resistance here. Same thing here when you have a 350 micron carbon fiber length. Now, the important difference between these two curves is, in case of 150 curve, you don't see a corresponding drop in the load, you don't see a change in resistance, okay? So for any drop in load, you don't see a big change in resistance. However, you see here, there is a drop in the load, okay? And you see a corresponding increase in resistance. Okay. Similarly, here you see a drop here. Okay, the drop you can see corresponding increase in resistance. So this can be seen very clearly in these systems. So this is a good a source of information for people who wants to use it for structural health monitoring. Okay, suppose if you have a structure subject to a mechanical load and you want to watch the damage inside the structure. You have a you can just monitor it. If you see start increase in resistance, then you can actually imagine that the crack is growing. Considerably. So you should take an action to prevent the catastrophic failure. So this data is very useful for structural health monitoring. So I want to briefly talk about dynamic fracture experiments. Whatever we have done so far is static loading, means you are applying load very, very slowly. Now, when you come to dynamic loading, means you apply the load, at very high strain rates, like impact loading. So we have a bar, we call this one modified Hopkinson bar. And there is a projectile here, which will make an impact on this, on this small copper pulse shaper. So when it's going to make an impact here, it's going to generate a compressive pulse. This compressive pulse goes here, and it's going to apply a load here. It's going to bend the sample. When it bends the sample, you start seeing the crack to propagate. Okay, so this is a high-speed camera. I'm going to show you in the next slide. We have a high-speed camera in our lab, which can actually do a beautiful job to capture the events, which are very fast. And then we measure the change in resistance by sending a current again. Using a differential amplifiers sent to oscilloscope. So we want to make sure that we trigger the oscilloscope properly. We use a strain gauge here, and also we measure the loading pulses using strain gauge as well. Okay, so this is the experimental setup to do dynamic experiment. Now this is the high-speed camera we have in our lab. It's a very fast camera, 10 million frames per second. We can take 256 frames with the exposure time as low as 50 nanoseconds, and it has a resolution of 50,000 pixels. Now, these are the images of high-speed camera. As you can see, this is the specimen, this is the bar, these are the supports. You only see one support here. When the bar is loading the sample, you start seeing bending of the sample. There's no crack initiation yet. You see crack initiation happens here, and then crack propagation happens here. The crack is propagating further. So this crack is actually propagating with a speed of 75 meters per second, which is not that fast compared to cracks that are propagating in plastics, where they propagate around 200 meters per second, 350 meters per second. Depends upon interface. You have more high speed crack propagation. Good. Now coming to the electrical data here, where we have this is the curve for electrical response with no carbon fibers. And here we have with 80 microns carbon fibers, this is 150 microns carbon fibers. So the x-axis is time, the y-axis is impact force, and this vertical axis is change in resistance. As you can see in this picture, the electrical response actually, there's a stage one, nothing is happening in stage one, but the crack initiation happens here. Okay, for the crack initiation at this location, the electrical response is very interesting because it actually decreases. As you can see, it decreases. Decreasing because when the load is applied, the specimen bends. When the specimen bends, the carbon nanotubes, there's no carbon fibers in this picture. So the carbon nanotubes come together so that we have a change in resistance, you're going to decrease in resistance. However, as you start increasing the crack starts propagating, you start seeing increase in resistance. You see very high value of resistance is 20% here. Now, if you put the carbon fibers, look at the crack initiation force. The crack initiation force is around more than 5,000 here, newtons. Okay, with no carbon fibers, the crack is actually around 500 newtons. So by adding carbon fibers, you increase the initiation toughness value by significantly by 10%, 20% there. But look at the electrical response. Here there's no bending because carbon fibers makes the composite very stiff. When it makes the composite very stiff, you don't see any change in resistance. Okay, pretty much you just keep the sample like this. Okay, then you have a crack propagation happens here, and you start seeing the change in resistance, which is around 20%, which is same as what you see in case of previous system. However, this is very interesting here, where the initiation toughness increases to 6,000, which is increase of around 1,000, and also again increased resistance as you see after crack propagation here. It's going to actually increase by only 3% maximum. The reason why? Because you have a good network there. When you have a good network, the maximum change in resistance is going to be always less, as you see in the previous experiments too. So that's the message we got from these studies. Now let me conclude this with the major observations. Natural fiber composites with CNTs, embedded epoxy, and microcarbon reinforcement demonstrate multifunctional approach, and they not only improve the interlaminar shear strength fracture toughness, but also have a piezoresistive damage sensing response. They can be used in structural health monitoring applications, as well as structural load-bearing applications, as well as structural health monitoring applications for both civil and military structures. So I want to thank NSF for providing us grants to do this research. I also want to thank my grad student, Sen Yan, who is a PhD student who had graduated PhD last year. I think I also have 3 undergrad students who did the research in this project. I must thank them too. With that, I'm happy to take any questions. Thank you very much.
Any questions? Any questions? Any questions to Dr. Vijay? Thank you very much, sir, for participating in this event.
Thank you. Appreciate that.
Yes, on behalf of Organizing Committee of the Chemistry Congress 2021, we want to thank you for insight presentation. Looking forward to meet you again next time.
Thank you. Appreciate that. Thank you.
Yes, thank you. Thank you very much, sir. Now we will have a 10 minutes break and join the event sharp by 1:30 GMT. Just we'll have a 10 minutes break. We will join by 1:30 GMT time. After that, Dr. Chahu from California State University of USA will join the event. We'll start our presentation. Yes. Yes, now just let us start the program and go with speaker sessions. Now we invite Dr. Chai Lobo from California State University of USA to start the presentation. Hello. Hello. Yes, Dr. Chai Ho, Department of Physics and Astronomy from California State University of USA to start the presentation. So no, next we'll go with the Dr. Cyprian Mio Sedutuin from Canada to start the presentation. Yeah, doctor, we have more four talks. Last four talks, Dr. Chahu from USA, Dr. Tingo Guo from Cyprian, as well as Dr. Ricard Huoga from Mexico. So any of four are present in this session, just you can start your presentation. Yes, yes. Okay, you can start your presentation, sir. Dr. Cyprian. Just you can share your PPT, sir. Yeah, dear participants. So we do have more 4 talks. Dr. Chai Hu from USA, as well as Dr. Tingo Guo from University of California, as well as Dr. Cyprian from Canada, as well as Dr. Ricardo from Saldivia from Mexico. Around 4 participants, you can join anyone and start the presentation. Actually, we are delay around 40 minutes. That's why we requesting if anybody are ready with your PPT, just you can start your presentation.
Here, now you can say something if you'd like.
Okay. Let me
Hello?
Hello?
Yes, madam.
This is Dr. Hugh.
Yes.
And I have to set up my paper first, okay? Before I talk and get my
Yeah, we can get it ready.
get the paper ready.
Would you like us to present now? Or would you like Dr. Hu to present now?
Yeah. Let's just get the paper number 2.
Yeah, let's see if he would like to hear you now.
Okay, yeah. Can you hear me?
Yes.
Okay. We will set up my slide. I must start talking, okay?
Yes, just you can share your slide on the share screen and start your presentation.
Okay, let's do it.
Yeah.
Yes, fine.
He's ready for you to present.
Oh, okay.
So let's get your slide.
No. You have to get the number 2.
Yeah. Okay. One moment, please.
Yes.
This one, the number 2?
No.
No.
No,
this one.
This is, yeah. Can I show this whole screen?
Yeah, we'll get there. Just 1 second. What happened to the Zoom?
This Mark here helping me out.
Yes, no problem. Take your own time.
Close this.
Okay.
Share screen. Here we are.
Okay.
Share. Okay. Can you see it?
Thank you.
Wonderful.
Thank you for the questions. Before I started this, I have to explain something that's very simple. First, the Stark effect. The Stark effect is a universal phenomenon. It's very simple. If you have a object that has a dipole or electric moment, which is most commonly the dipole, and a charged particle comes in the field of a charged particle. Well, let me go back a little bit. Normally, when a constant electric field goes through this object, and this object will go to a higher energy level, absorbing energy. That's constant electric field. So that's everybody understand that. High school understand that. The only difference we're talking about here is that field, that electric field, is not a constant electric field like in high school physics, but it's a moving charge. And so, for that, the moving charge has the same effect on the electric moment of the target. So In this case, they were already connected together as one system, and because the potential energy changes. Because when the Stark effect here is now they have a mutual attractive potential energy, so it's become one system. So in that field, there can be resonances, just like the classical case, because at certain energy, and suddenly there's a singularity, like
Yeah, you can scroll down.
like up here in this diagram. This is and so I will explain this later. This graph is a scattering matrix in real form, we call tangent phase shift. You see this spike here. So this comes from a calculation with a three-body system, positron on hydrogen. It has, here you have one peak, one resonance, another resonance, another one here get cut off by the energy we choose here. So there are three resonances in here. And this comes from a solution of the Philadelphia equation. And that has, that's able to calculate all different, separate all different channels of the scattering power. So we'll come back to here. Let's come back to this my explanation of these resonances. So this resonances is just a Stark effect like the classical one we taught in high school, except it has its resonances when the charge moving at certain distances. So after that, and I will spend a few more words on what I do. We're doing three-body calculation. In this graph comes from, as I said, a positron plus hydrogen scattering calculation. And it has 6 open channels. And so the Philadelphia equation is to be able to separate each channel out, give you a wave amplitude for each independent channel. That's the advantage of that. So this is a big calculation. It involves it involves involve 500,000 coupled linear equation. We're solving, after breaking them down mathematically, we solve the Philadelphia equation with 500,000 coupled linear equations. So it's a big calculation, and I occupy the whole computer, most supercomputer. So we'll come back more to this calculation. So let me explain some more about the Schrödinger equation. The difference between Schrödinger equation and the Philadelphia equation is, after you add all the three separate, separate channels in a Philadelphia equation, it's equivalent to Schrödinger equation. But Schrödinger equation have only one one solution, one wave function. But this one has 6 independent wave functions. So that's a big difference there. And another problem with the Schrödinger equation is for this 3-body problem, and you have a totally Coulomb degeneracy, we call. That means for the hydrogen atom, for example, energy depends only on the quantum number n, and proportion of 1 over this n square. And for each n total quantum number, all the energy levels independent that are all degenerate. We call that Coulomb degeneracy. So all those states belong to the same n and has the same energy. That's called Coulomb degeneracy. And the wave function, the wave function has only one solution instead of 6. That's a big difference. Not that reversible physics, you say, what we're there. But that degeneracy carried too far by most people. They forgot about their other small things you have to include it in it when you do precise calculations. That everybody knows what fine structure is, right? So there's a small range of energy above each n energy level, and that is no longer degenerate when the fine structures turn on. That's where the problem is. That fine structure, energy level, when you have a fine structure, the degeneracy is partially removed. So you will find the energy level above each n threshold has a different, let's say n equal to 2. They have a number of energy levels due to fine structure. But the fine structure has a very, very narrow energy width. So most people just ignore it, or it doesn't show up in your calculation because it's so small energy range. And if this phenomenon we're talking about here, the nature pickup phenomenon is happening not energy region. So all these years we've been totally ignored that part. But this phenomena only occur in that narrow energy range. Otherwise, we could have this done 30 years ago. We already solved lots of problems. So after that, so that's the difficulty. Why such a simple phenomenon have to wait it for so long until the computer is big enough to be calculated, and that's caused most of the problems. Sure, some people still believe this phenomenon doesn't exist. It exists only in that very narrow energy width, just above a new threshold of n. Now, after that, let's start come back to what we want to say.
You want to go to the top?
Okay, let's just show them. So this phenomenon we call it nature's pickup reference. It used to be called a different name, and but that name is hard to say. But I think I major were changed to this. It described it more physically. So here we are going to give you some examples what that phenomenon means.
I can scroll down.
Okay. Now let me now let's talk about nuclear fusion. But not all nuclear fusion comes from, of course, there are different ways you have low energy nuclear fusion. But not all come from this phenomenon, of course. First, let's talk different nuclear fusion, which does not come from our effect. This one is a nuclear process. You have a proton collide with lithium-7, and here are the energy levels. So this just shows you the different way you can have nuclear fusion first. And here, this diagram I take from a textbook by Professor Evans at MIT. And I still remember it when people talk about fusion, I look back at this diagram. Here is an energy level diagram of barium 8. And here this energy level is we call the breakup from here to here is a breakup energy. If you want to take one proton out of this, you would take this much energy. Okay, so we call that the separation energy. Now you can see if you have a proton coming on lithium-7, and they are touching this energy level. This is the energy level of the barium-8. This one has a very the width is about 3 MeV. So if you have a proton come in a little bit above the separation energy, there will be this compound energy level. So this compound energy level from here to here is a width. You see, it goes. It has a 19.9 MeV. It goes right from here to here. So it breaks down right into 2 alpha particles. All this energy is spread in these 2 alpha particles. So this fusion, however, have an undesirable effect, because each alpha particle, you see, even if here it's unlikely the energy can get up there. You should just get slightly a little bit above here. And it's half of that, more than half of this this energy level. So that's all it does. The fusion comes from the nuclear energy levels by itself. It doesn't need anything to help it. So the only trouble is that this has a huge energy. If you energy around here, the energy is about 10, a little less than 10 MeV each. That's that's a huge. That's not a something you can use in your put a generator in your house to use that energy. So that it's a difficulty to use as an energy source for us. And but this does appear in nature. Even now, if you can get into trouble if you carry lithium, you can get into that kind of problem. You have a huge alpha particle come out. So this just shows you that there's another way you can have nuclear fusion, but not the way we can. Right now, we will use this in a battery. You have to be very careful. If you use in the battery, you have to be very careful. To avoid this problem. So that's it. Well, let's go back to the original purpose. We want to explain the fusion comes from the Stark effect.
Go up.
Yeah. Oh,
Sorry.
oh, okay. No, let's get
Or
rid of it. Done. Okay. Now let's talk about diffusion on lattice.
Would you like up? Oops.
Oh. Okay. I'll talk about estates. Well, this is another name for that. For the for the resonance. Well, this one is good for energy use because it doesn't produce any energetic nuclear particle. It produces just heat. That's exactly what we want in our house. And so let's pay some attention on this one, how this resonance is one initiated this kind of calculation. So let's consider this pickup resonance. I used to call them, what is it, lattice resonance, because this guy is the first physicist back in a long time ago. He found some indication of problem in this area. He doesn't know exactly what it is. So let's consider what's going on in here using this model. Here is a diagram. Is a deuterium bound in a lattice. Now this is what happens when they are in resonance. When this deuterium come in, and they want the deuterium that bound to the lattice is represented by this thing, because it's bounded to the lattice is sensor different. This is an incoming deuterium with proper energy. So you will resonance it cannot here. And this resonance is also called quartz particle. Now, so this part, this is a guy inside the lattice, and the particle come in is now at the resonance. So what we mean when we at resonance is it suddenly gets stopped. I want that diagram. The top one, the first diagram. The top. Yeah, I want. Yeah, it suddenly stopped. The angle dropped. It should come in this way. It dropped drop 90 degrees. And after gap, it jumped to another 90 degrees. And then you drop down. So this is a whole life of a restaurant. So first come in, why does this? Why drop 90 degrees? It must be something happened to it, right? Now something is a tremendous repulsion come from the guy sitting in a lattice. It's a tremendous repulsion. Then it stopped it to move anymore. So when it stops it to move, what it does, it takes all the energy away. And during this time is that process. During this time, the incoming particle become a wave pocket because it has no more energy. Energy taken away. This is the life of the wave pocket. Now here we are. Let's go back down there. Fast. Yeah. Okay. Now. This is a S wave. Very, very nice. Everything is spherical symmetric. So the wave pocket. This is centered here. The wave pocket is a wave pocket with this width. The maximum is here. It's a spherical surface now. So the whole wave pocket at any moment has a width from here to here, okay? And because the wave pocket is, original wave pocket is formed here, but the extent, as you know, the wave pocket has zero energy, but it expands both ways. This is expanded as well. The whole layer of cell, that's the way, this is the front, this is the front, this is the front. They expand both this way and this way from the original pocket centered here. Okay, and then so all this from when it's expand, and it is you can associate it with the previous graph, and by the time when it drops, when that drop to after the gap, remember this after there's two infinity peak, and after that this eventually this will goes eventually this will move too, okay? Because in a gap we have there, this will move. So eventually this will crossing into the center, the other deuteron. Eventually everything collapses into there. So all the wave pocket going to collapse into this. Let's go up. Let's go quick enough. Yeah. I should put that together. Oh, it goes down here. So it's finished. So they're together now. They stick together. What after that depends on the lattice. So after that, now we're at this point. Now I'm going to discuss what happened to the deuterium. So the deuterons are come together. They are one quartz particle. And now here the energy comes in. It's a quartz particle of H2+. So this is a quartz particle. So one system actually. Now, so what happened to the, let's look at the energy of the system. This energy diagram shows you, here is this is the energy of this energy level. Now let's look at the energy level coming here. Now, here the energy, the quantum number, the two quantum number for the nucleus, 0 plus, 0 plus. Can we find any 0 plus or 0 plus here to get in? Nothing, right? Nothing close to that energy. That's a quartz particle now. Nothing close to any of those energies. So they cannot get into an energy level of the alpha particle. Okay. So what they can do is sit there, but when they sit there, the energy level is way above this. You say they have the exact same quantum number, right? That's where the quartz particle is. They have the exact same quantum number as this nuclear quantum number. So they cannot go. They cannot use any of those excited energy level to just drop in this drop to the ground state. So what they can do is just set their leak energy, but because it's too much energy. But so it's like a dam. It just sits on the top. And but since it's certainly not in equilibrium, there's so much high energy in there. So they have to find a way to get rid of the energy, if you can. If there's a chance, they will get rid of the energy, right? But you see, when this guy still setting in a lattice, remember that the quartz particle still setting on a lattice. But they figure so the energy can leak to the lattice, like a small little hole in the bottom of the big dam. They leak that energy. That energy leak is of the order of photon, right? The vibration energy of the lattice. That photon energy is so small. Can you compare it with any of those energy with the photon? So it's nothing. So that energy is nothing in nuclear physics. So that energy for nuclear physics is already in a corresponding limit. It doesn't follow those energy level things. So it just leak. Every time you accumulate a photon's energy, you just leak to the lattice. So it just continue leaking. Take a long time. That's why usually take days, because it's such a small energy. So, but if too much energy for the lattice to hold the quartz particle, it gets kicked off. It's get kicked off as a quartz particle now. They can be freed as a quartz particle. But when you can get, as long as it get off the lattice, and you get into the electron cloud. There's a lot of electron, very dense electron. So the dense electron were surrounding them and bumping and keep eating up their energy. So eventually they become the alpha particle. So eventually it become an alpha particle. But probably have some kinetic energy, but not that much, because a lot of them just dissipated with the electron cloud and produce heat. It doesn't produce much but heat. So that's a whole story about this. It's very easy to understand and nothing complicated, just conservation of energy. And of course, you have a corresponding principle because energy leaking is so small, it doesn't follow any of those nuclear energy level diagrams. It's a classical energy leak from a whole bunch of energy. Slowly. Yeah, because it's a crowd, just collect part and bounce off. So that's why this energy is very slow. And but it's good, nice and pure energy, heat. You don't need worry about any particle or any radiation of any kind. So whatever we can make it to work, I think it's worth it. I think there are a couple of groups already made a lot of progress. Hopefully we can use that energy and we don't have to worry about the radiation. So this is for this problem. So I hope that's clear enough for everybody.
Scroll down.
Okay, let me see.
Okay, now.
Okay, so we have now there are many other cases. I want you to, instead of here, you can I will give you some reference down there to look at, and there are many more references. But there's one more thing I want to include in here, because this is relevant to biology, I think. Well, this is some calculation and extreme data a long time ago by this group in San Diego. It's a big group. This is a positron. You very low energy positron. You use very low energy positron on a big huge molecule. These are non-chain molecules. I think it has something to do with biology. They find those positrons usually they just pass by, but some energy suddenly the annihilation goes up thousands times, and at the same time a vibration level is acted up. So those huge annihilation peak, and probably is come from this resonance. Because if your energy is right, and suddenly it will catch one of those electrons and annihilate it. And at the same time, when you click on the molecule, you set up a vibration. And so people have done some calculation. They notice there's something going on. They call that gateway. You know, they call it vibration doorway states. they have some data there. They fit some resonance fitted. So that's it. They call that a vibration doorway state. And this is one of the vibration energy level of the molecule. And unfortunately, they didn't have anything information about the gamma resonance, so it's difficult to make a qualitative calculation on this one. But they do have that, they call that doorway energy. So they all come in pairs like that. And so at that point, usually the particles just pass by, but those energies come many orders of magnitude large. So I think definitely it looks like that comes from this resonance. And now, so I want you to look at this reference here. This one did a big calculation that we solved a half a million by copper linear equations, and they have all the diagram and everything. And do we have a time? We maybe can get another one to show them the diagram. How much time we have left? I think we have some.
I don't know. Yeah.
We
can share another diagram on your desktop if you want. Yeah.
Yeah. Well, let's look at another diagram. So now please look into this. People are interested to start a calculation. Look at this. Look at this reference, and this is another calculation you should look into. This one is more. They have more examples, more pictures, and this one is a complete one. If you want to look at this, so let me show you some more of the pictures that leads to this.
Okay.
Let's get another.
Okay.
That's
I have to stop the share and then we open up another one.
Oh, okay. We're going to open up another one to show you some more. Okay.
Yes.
Which one?
I think it's this one.
This one?
Mm-hmm.
That do it?
Yeah,
no, I don't think so. Wait, hold on one second. Share screen. This one.
Yeah.
Oh, here we are.
Okay.
Yeah, that's it.
Okay. Now let's go to, since we have some time, let's go to a little more, show you some more of this thing. Original, this calculation is done in 2002, and we calculate the antihydrogen formation cross-section for the S states, and we calculate from the NPS n equal to 2 to H bar n equal to 3, the whole energy region. The whole energy region, we calculate the cross-section of this cross-section. This partial cross-section. P bar plus H2 goes to this. So this is try to produce antihydrogen. So for this energy gap, these people found already. These people find already, but they don't know what this is. They think I made a mistake. They think this must be, nobody find it must be a mistake. Okay. So I cannot tell them what until I can prove it's not a mistake, right? But at that time, the computer is too small. So I have to wait till the computer gets bigger. So that's 10 years later. I still cannot believe that's some kind of stupid error, because it was a very, very careful calculation. Nobody nobody see anything in this area. It just goes, nobody see any structure in this area.
All right, go down.
Okay. 10 years later, we did a big calculation. As big as a computer can accommodate, no more. You use the whole thing. We calculated the energy near the resonance. We have 3 calculations, I think. These are the K matrix. What is a K matrix? K matrix is just a T matrix in real form. Okay, and this is one of the energy. This is relative to ground state. This is relative to the PSN equal to 2. So that 2 different measure levels. It's very small energy. So very small energy above n equal to 2. And this is the whole K matrix, cross-section and K matrix. And this is another one. This is one of those energy. There's 3 of those peaks we calculated. Cross-section, K matrix. K matrix is just a real form of T matrix. You see how small this energy measured from, this is measured from a PSN equal 2. This is measured from ground. So this is very tiny compared to that, you can see. So most people just ignore this. And this is how the actual wave, this is the wave, how the wave function actually looks like. This is 3 peaks. So this is the intra channel. P plus PSN equal to 2. P state. Now this is one of those one, not exactly on the resonance. This is the resonance peak. This because the energy is a little bit off, so they drag a tail with it. But that's not a big problem because this kind of resonance has some unique property. The width is equal to the wavelength that you can prove. Well, this is one of them. This resonance is, you got every piece of the resonance here. And the third one, I only get half of the resonance. Because I cannot increase the size anymore. Because that's about take up the whole computer. And otherwise I would go more. So here's actually this is actually the other one is the first resonance. This is the second. This is the third. And this is the wave amplitude, the Philadelphia wave amplitude. It's so it's just a wave function, but independent. No more than the Schrödinger equation. All those lumps together into one. But when you solve the Philadelphia equation, you can solve each independently. Well, not independently, they're coupled together. You solve this coupled equation. You get the wave function independently. Each channel has its independent wave function. This is it. So they this diagram established the following equation. I keep this matrix here, so I can always use that for comparison. Can I go faster? Okay. So this comes from that calculation. This diagram from that huge calculation. That calculation is solving a linear equation with about half a million by half a million. And so I cannot, the computer is not big enough to do anymore. Otherwise, I would calculate more. This calculation was carried out in 2012 and 2011. Of course, now you can do much better now. I hoping somebody going to keep doing this calculation, but nobody did all these years. I'm still waiting for somebody to continue the calculation, because now we can do much better. And so this diagram comes from that calculation. So you can see there's two resonance here. The third resonance is cut off practically. And these are the two complete resonances you can see. And it's let's go back to the wave function.
If you scroll down.
The picture. Oh, let's get it to the second one. Okay, this one. This one has the largest cross section, and I had to do some extrapolation to get to the point. This point, because I cannot get the computer to do anymore. And some review thinks this is just a probability. This is actually a wave function, Fedorov amplitude. But Schrödinger equation only have one of these. And we used because we have short energy, we used two coupled equations for this. So this is this channel. This is here's a PS in equal to 2. Here's a incoming photon. And this one is actually has largest probability for these calculations. So hopefully somebody can do this calculation. This is we solve the Fedorov equation in a configuration space. I think this tell you much more. You can plot the wave function. The wave function actually tells everything. Remember, you used to tell you the Schrödinger equation, the wave function tells you nothing, but the average, this tells you everything. all the detail of the three-body process. And then somebody complained about the Fedorov equation. But every method has some kind of shortcoming. If you look at the right parameter region, that's what I want to say next. If you look in the right parameter region, oh, by the way, the Fedorov equation, which we solve is a modified Fedorov equation. It has 3 parameters in there. So if you look in the right parameter space, you can avoid any other problem they call it the theoreticians are worried about. You just have to look into the right parameter region and to get the right wave function. Now, I hope people pick up this. Everybody want to do the easy way. They want to use the Fedorov. They want to use the use instead of configuration space. They want to go to the momentum space. But the only trouble is you lose a lot of physics there. The wave function tell you more physics than anything else, unless people use the Schrödinger equation. Wave function doesn't tell you anything, just the average value. But this Fedorov wave function tells you everything. Everything is in the Fedorov field. And there's more of those things you can read in some of my references. And they should calculate, somebody should extend that calculation. I'm too old for that. Somebody should pick up this. I prefer this configuration space calculation, which tells you a lot more. And Norton's calculation, they missed the basic thing. And so I would like somebody like Norton's method easier because it's easier to do calculation. But the physics is all in the wave function, not in the momentum space. And the wave function starts everything, has all the properties. Instead of looking into complex pool and everything, that missed a lot of physics. Now people like the momentum space because it's easier. Doesn't take so much computer time. But if you start from the basic wave function, which contain all the physics in there, you can see it. So I hope people pick up this calculation, and you can use the momentum space calculation. I say together, that would be best. So, any questions? Anybody want to ask any questions? Nobody. Is anybody there?
Stop the share.
Any questions to Dr. Chaihu?
I want to share, right?
Yes.
Any questions? No questions?
Any questions?
No question. Can I give you some opinion? Somebody should do the calculation. It's not hard now. With a computer, 10 years the computer is much better. I am too old. Otherwise, I would do, but it's hard.
Yes, we do understand. We do understand, madam.
Well, it's
Yeah.
not easy for me because I sleep too much.
Yes, yes.
I need a lot of
Yes. Any questions to Dr. Chaihu?
before I do have to. I can work 24 hours. Now I can work 4 hours.
Yes, yes, we do understand. We do understand.
I wish somebody would pick up the calculation because there's lots to learn.
Yes, yes.
Especially now we're going into the area in the multi-discipline area. You can have this kind of resonance in any system.
Yes, yes.
I'm suspect even in virus, and it looks like that way.
Yes.
Yeah. So I hope really people have to do this, and there's so much you can learn in the microscopic region.
Yes, yes.
Wave functions.
Thank you very much, madam, for your participation in this event.
Yeah. Any questions?
No questions.
No questions. I have a few minutes left.
Yes, no one is asking the questions.
Huh?
No one is asking the questions.
Nobody has any questions? Well, I hope people pick up the calculation. And there's a lot you can learn for different systems. I'm telling you, even for virus, even biological system, it's there. It helps solve a lot of problems. Because there's a lot of problems. We could have used nuclear energy 30 years back if we had this mechanism.
Yes, yes.
Look how much delay our progress because we didn't know this mechanism.
Yes. Thank you very much, madam, for speaking up in this meeting and providing a unique perspective. Thank you for sharing your tips with us.
All right. I hope somebody do more calculation on this thing.
Yes, no one is.
And so we can understand more how it works in the microscopic system. And maybe
any questions
we
from the
can
participants?
We can fix the virus problem forever. Can you believe that?
Yes.
Yeah, if you know the mechanism, you know how to fix it. If you don't know the mechanism, like the nuclear physics, we've been waiting for how many years? At least 30 years. And in between, people talk, there is or not, this or not, it's or not. This might spend all time arguing instead of doing anything. If we had learned just even a few years back, we could be using the nuclear energy right now. And then we could stop the virus altogether. Yeah. The virus has used physics. Ever since physics. Yeah. And you have to put physics together with different disciplines.
Yes.
That's how to solve problem. And we should do that now.
Yes, we need to do.
But I'm disappointed when I started this wave function. We solved that wave function in 2012.
Yes.
Yes.
We will forward to you your email ID. Thank you. We will forward to your email ID.
Sorry, could you please repeat that once more?
Louder.
We will forward to your mail ID.
Oh, okay, sounds good. They will forward questions to your email. They'll
Yes.
see.
Oh, okay, good.
Yeah.
Yes.
Okay. Very
Yep.
good.
Yes. Apart from this, just you can text you can text again your queries on the text chat box. I can ask. I can send through your mail ID.
I couldn't understand that either.
Yes, we'll be sending to your mail ID, sir.
Louder.
Okay, they'll email Dr. Hu if they have questions.
Oh, yeah, yeah.
Okay.
Sure.
Okay.
They're
Thank
That
you.
sounds great.
They're
Okay.
welcome. I like some more action on this.
Okay.
Thank you very much, madam, for participating in this event.
People just
We'll hit the mute button now then, okay?
Okay. Thank you.
Okay. Thank you.
Looking forward to meet you again next time. Yes. No. Now we ask Dr. Thingu Guha from University of California to start the event and start presentation.
All right. Well, can you see my screen?
Yes, it's going to start, sir.
Can you see my screen?
Yes.
Okay. All right. Well, thank you for the invitation. And my name is Ting Guo. I'm from UC Davis. So I would like to switch the topic a little bit, although I do agree very much that physics and the math and eventually chemistry and other disciplines are all important. So here I want to talk about something probably new to all of you, which is called X-ray nanochemistry. And I'll explain what it is and what we have been doing and what others have done, etc., and possibly what could be done down the road. So you can hear me all right, okay?
Yes.
Right?
Excuse me,
all right.
just to kindly share your presentation on the screen share.
Oh, so you can't see it. I was asking you about that. Let me see, screen share.
Yeah.
All right, can you see it?
Yes.
All
It's
right.
going to start.
Yeah, let me do that.
Yeah, it's fine.
So yeah, so it's about a new discipline. I call it X-ray nanochemistry. So I'm from UC Davis chemistry, and it's been going for about 20 years plus. And so I'll talk about what we're doing right now, what's been done, and what could be done in the future. All right. So certainly the first thing pops up probably in the mind among all of you is, why do we use X-rays, right? So there are lots of photons in the UV vis region and etc. X-rays are very unique because it's been there for about 100 years, over 100 years after it's first discovered. And the two general or most prominent properties are, first of all, it's highly penetrating. And the second, they don't almost have no diffraction limit. You do have diffraction from X-rays, which is why you have a crystallography, but those are on the order of angstrom, right? So it's energetic. Sometimes you hear about gamma rays, which is high energy rays, or medical X-rays, which is up to 10 MeV. But normally when we talk about it here, X-rays, if you don't have any adjectives, it's from 10 to 100 kilo eV, right? Think about a visible photon is about 3 eV. This is much more energetic. And that's why it can penetrate. Well, also it's a photon, so it's not charged. So that's why it's very highly penetrating. And the diffraction limit can be below 0.1 nanometer. So basically, only the atoms or molecules would be able to diffract. And in free space, X-rays would just go as if there's nothing, right? Photons or laser beam will eventually expand. So X-rays can be used in many places. At many places, you know, you saw these airport. Well, you don't see that many more or too much more because we don't travel as much. And you can see through the body. So this is medical images. And in medical image, they invert the absorbing part and the non-absorbing part. So non-absorbing part would look dark and absorbing part would look white, right? So that's the opposite of other, say, films taking images more light. You have darker places, right? Because of the photo receiving part, the reactions. And so beyond these imaging capabilities, there are also a treatment, right? This is somewhat already being discovered right after X-rays were discovered, because they realized, well, after certain images, the skin start to blist. And so then they discovered the killing part of X-rays, which is why it's called ionizing radiation, because it does not really scatter much, but it does ionize, especially when the energy is matched to the core electron energy levels or ionization potential. And these are all real space. So you can go to reciprocal space, which is how people can see diffraction patterns. This is a DNA, which is beautiful, right? So you can have an X-ray. Although these crystallographers or crystallography generally use very low energy X-rays, so not even 10, possibly even 8 from copper, 8.04, right? So that's highly stoppable by some maybe 100 micron thick water. Right? When you go to 100 kilo EV, that's not the case. So X-rays are powerful everywhere. So if you go outside, you know, even at home, if you eat bananas, right? So there are all sorts of rays that's going through your body all the time. However, it's not very obvious that we have utilized, or it is obvious that we have not utilize X-rays to our advantage, because we have not explored how to use X-rays to drive chemistry, right? So that's the reason we want to develop X-ray nanochemistry. So if you look at how photons in general react with or interact with species materials, right? You have atoms, molecules, metamaterials, bulk, right? So all sorts of things. The photons do interact with them a lot, right? So the photons are generally from 100 nanometers to 2,500 nanometers. So this is a mid IR. This is VUV, vacuum UV, right? So the absorption occurs to the photons by the molecules, right? So there will be fluorophores and other things, and even more prevalent are these chlorophylls, and so they take photons and then energize some molecules, right? And then that energetic molecules would then provide electrons or protons, right, to the mechanisms in the plant cells, or even in the skin cells, right? So that will drive the production of different molecules. In this case, can take CO2 and to produce oxygen in plants. And in our case, in our skin, it can produce vitamin D, right? Which is very difficult to be incorporated into the body otherwise. So the photons can do that. The question is, can X-rays do that, right? So we can generate or create this photochemistry for X-rays. If you see the rest, you will see, okay, mostly it will be involving nanochemistry. So that's why we call it X-ray nanochemistry. And as the previous talk alluded, that everything is about electrons, right? So electrons. Chemistry is just 100% based on electrons. Yes, you have protons, you have other things, but nonetheless, the photons interact with the electrons and the reactions involving electrons, right? So that's just the key. And X-ray nano is the same thing, right? So it is X-ray nanochemistry, starting from the understanding of X-rays interacting with matter, which is interacting with electrons, right? Photons don't normally interact with nuclei due to the Frank-Condon principle, but sometimes they do because there's always exception or exceptions. And so ionization, Compton scattering, and ROS, reactive oxygen generation. So let's take a look at it, the electrons. So first of all, you have photoelectric. Photoelectric is you have a core level filled with electrons, and that electron would sense the presence of the X-ray photon, right? And then be ionized, meaning it gained enough energy to become a free electron, right? So that's the photoelectric effect. And the efficiency of that is proportional to the Z to the fourth. So that means the heavier the elements, the greater the photoelectric effect cross sections. Right, so once that hole is produced, for example, in gold, right, with the Z is 79 compared to carbon like 6, carbon is 8, right? So that's almost 100, 10 to the fourth. So that's 10 to the fourth, right? So carbon is 10 to the fourth less absorbing than gold. If you have one electron, right? So once that hole is produced, it will be filled because that's energetically unstable, and the filling of that would cause the generation of Auger and other secondary electrons. So it's like you try to take popcorn from the bottom of the popcorn machine, it will explode and bring up other popcorns, right? So, and there'll be other processes like Compton scattering, meaning the electrons are almost free and X-rays can still interact with that. However, the general consequence is X-ray will lose some energy and that electron will gain some energy. So you have some energetic electrons with slightly less energetic X-rays afterwards. So that's prevalent in low Z elements because the binding energy of the electrons in those elements are much lower than the binding energy in heavy elements. And they have pair production, which is if the energy of X-rays is greater than 1 mega eV, it will produce a positron and an electron, right? With 504 kilo EV each. Right, so that's a specific thing that nuclear physicists figure out. Okay, so then besides of these primary processes, once the electrons are produced, then you have other things such as reactive oxygen species produced. And so it's simply as the electrons produced here, ionized water and recombination of water or subsequent dissociation would cause the generation of many things, such as not singlet, but oxygen atom, hydrogen atom, where's hydrogen atom? Somewhere, and OH radicals, hydroxyl radicals, hydrogen peroxide diradicals, and you have solvated electrons, and you have superoxide, which is oxygen O2 minus. Right, and because of these presence of these 5 primary radicals reacting with any other things very quickly, you get even a single electron is produced in water, you have up to 80 different reactions. So this is not a trivial thing that you can predict, right? Even if you want to predict, this is very difficult because of its unpaired electrons, so it's not closed shell. The HOMO-LUMO would be almost 0, and then it's very reactive. So not only energetically, it's not stable, but they're very labile. So it's a nightmare for I guess theorists and experimentalists. However, we don't deal with that much because we can use chemistry and physical models to isolate and try to figure out if we can eliminate, let's say 75, can we study the 5 reactions? So that's an advantage of being an experimentalist, because we can isolate. I do theoretical work as well, because even if you isolate things physically, you still want to understand everything theoretically, because otherwise you don't gain anything. So theoretical understanding is the ultimate goal, but you want to isolate simple things to try to understand something first. So here is what we think we can do. We can put a really heavy element nanoparticle. So one atom would be too small, too little, but we can aggregate a number of atoms to make a nanoparticle. This is a gold nanoparticle, maybe 10 nanometer, 100 nanometer, right? And if you compare the absorption of X-rays by gold and water, you will realize near the 100 kilo EV region, the difference is about a 2 order of magnitude in terms of absorption coefficient, meaning per gram, or not per gram, per centimeter cube. No, per gram, yes. Centimeter cube square per gram. So this is 2 order magnitude. If you factor in the density, the difference will be like 1,000, right? So gold is about 1,000 times more absorbing than water. However, you do realize gold also is heavier. Gold is much more expensive than water. So you can't use too much gold, right? Not everywhere. And in terms of attenuation, this is 1, they're about the same, and water and gold. So if you compare for about a 1 kilo EV, gold and water absorbed about the same. If you go to like a mega EV, they're about the same. Just here, they're different. So that's very strange, right? So here it's about the same, but here there's about 2 order magnitude more in terms of absorbing or attenuation. So the absorption is what's absorbed by material. Attenuation includes the photons being scattered, which are not absorbed, right? So there's a difference between attenuation, the blue, and absorption of the red. And what we care is the absorption, not the attenuation, right? Because attenuation, there's some photon escaped. And you can divide these processes after absorption into different other smaller processes. So here it is. And so we can divide that into physical enhancement and chemical enhancement and possibly other enhancement. So let's think about this process. So X-ray, let's say a photon, let's say it's absorbed, because there are a lot of photons would go through this material, gold particle, without being absorbed, right? So let's say there is absorption and it only occur to an atom, although you can argue that that's not the case. There will be other interatomic Coulomb decay processes, right? But let's set that aside. Let's say there's an X-ray photon absorbed by an atom, and then there's ejection of an energetic electrons, such as a photoelectron, right? So that electron would just travel in water or somewhere, right, as solvent or surrounding, and produce ROS and other species, and eventually be stopped. So let's say this passes long, so we call that average effect or type 1 physical enhancement. And there are other OGA electrons, secondary electrons, they don't have too much energy, so they deposit energy near the surface of this nanoparticle. So we call that type 2 physical enhancement. Type 2 physical enhancement. And there are other processes like chemical enhancement based on catalysis, because there will be radicals produced elsewhere, react with something and form a radical intermediate. And that intermediate would be converted into product catalytically by the surface of nanoparticles, right? So you have physical and you have a chemical. And also the radicals can be scavenged by the surface, because this is catalytic active and this is very reactive, so that it can react and basically take it out, right? So it does not react to the species you want to react to. So that's the general thing, and there's biological, I'll talk to you. So here is another look at this process. So the physical, meaning electron coming out, generate the radicals. Radicals react with things like DNA strand, right? So that's the physical. And that's enhancement, because without the gold, there will be no such radical. And with the gold, there will be extra, and so it will react, right? Chemical enhancement is, well, if you have another particle here, and then catalytically, this strand may be broken, right? So that's chemical. And possibly there's biological. So if there is a repair protein, generally it can, if there's DNA breakage, generally this protein can just swing by or just hop on and fix it. But if you have particles somewhere there in between, then it cannot do it, right? So this one does not directly damage anything. So it's not a physical, because it does not generate the radicals. It's not a chemical, because it does not catalyze anything. So it's something else, only exists in biological processes or organisms. So that's another way to look at it. So we've done this since 20 years ago, and we submitted first proposal about 2001, and then we progressively make more discoveries, and along with other people, right? So this is my group. Heinfeld is not mine, but they published the first paper a couple months ahead of us. Although we had some problem with our publication, the first one. So, but nonetheless, the first publication was 2004, 5-ish, and then right now it's much more. So there are about, I think, over 200 groups in the world working on this, and I think it'd probably be 700, 800 papers published. So this is a number of publications, as you can see, starting from 2004. This actually is not nano per se, but you can say there's 1 or 2 papers touching this area, and the takeoff is mainly around around that there, and then right now it's continuing. So basically, X-ray nanochemistry is to use nanomaterials, nanochemistry to increase the effect of X-rays. So I was naive enough to write a book about it. It took me 3.5 years, but it's a good exercise. So no matter how old you are, you can still write a book to summarize what others and you have done, which is different from a paper, but nonetheless, I think it's a good document for me to constantly go back and read a section. And so X-rays is critical, but the materials more important. And I don't say just the materials like materials science, but it's actually all sorts of the chemistry, organic, inorganic, bio, etc., everything. And right now there are a lot of things we need to do because of this discovery and the opening of the discipline. There are a lot of instrumentation we need to work on, etc. And certainly the most important thing is the applications, right? So because if it's not of no use, still have some theoretical value, but if of no practical use, then it's not too good. So, but as you will see, the application potential is huge. So this is again, we have the particles and the physical, chemical, and anti-enhancement. So I'll briefly touch on those and give you some examples. And one thing we are working on is to not to use these particles in the open, because that's most people do. And it is very hard to control. If you do nanochemistry, you understand the surface chemistry is very rich. And if you put that into the cell or some reactive environment, the surface will modify it. So what we want to do is put all the reactions in a shell and then do it that way. And we have done that. And these is just silica particles with some pores, and you can make them and you can put molecules in. We're making a second generation, so it's more complicated than this. And then eventually make them into machines so that we can close open at will. We're also doing some instrumentation like this scanning focusing, because you probably heard X-rays cannot be easily focused by lenses, right? There are other X-ray focusing optics like fiber taper and other things, but nonetheless, it's not easily be focused. They cannot be. However, X-rays have very low diffraction limit, so you can aim at it, and you can aim at it while rastering this position, right? So you generate effective focusing, and this is demonstrated by us. And so basically, this is a film, and you can see the X-rays here is very light, here is very intense, right? So the increase is about 100 times. So if you have these physical, chemical, biological enhancement, and if you can combine with this X-ray focusing, you can easily deliver 1,000 times more X-rays inside the body, right? So, and then the skin. So which is the Achilles heel for X-rays, because generally X-rays would be absorbed by the skin first or the most. And so people then resort to protons and other things, particles, but they are much more expensive and difficult to deal with. So if you can use these 100 kilo-EV X-rays, you can have like a diode, like the size of your small finger, pinky, right? You can make an X-ray tube like that, and it goes to 50 kilo-EV-ish. And so I think X-rays have a lot of advantages. And this is a blow-up picture. And X-rays can drive reactions. So this is the one we published a long time ago, but we're in the progress of making much better systems. So this is basically you have a nanoparticle, you have some kind of model drugs linked to the particle through DNA, and when there's an OH radical produced, then you can cleave that and release. So we've done that in the cell model, and we've seen enhancement, and you can release model drugs or even doxorubicin, as we tested in mice, and here's the result. And so basically there's some effectiveness. However, as you will see, we are not resorting to these type of simple systems to say deliver drugs and then release drugs. And so this is a blow-up picture of a particle linked to the model drugs. In this case, it's a FITC, so it's a fluorescent molecules. Normally, if it's linked to the gold particle, then it's quenched. Fluorescence is quenched. And if it's cleaved, then you can detect the fluorescence. And we've demonstrated that you can do this without anything else, because this guy the surface still scavenging. So actually there's a counter productive process is working towards it. They release some OH radicals, but also scavenge OH radicals. And OH radicals are the things we need to cleave the DNA to produce drugs. And we did something similar using a protein. And so then the purpose is then we can engineer proteins to release from the surface of particles and then do other things. And we've done this a couple of years ago, and we're improving this system as well. So in this case, you can compare the gold particle inside the shell versus the shell versus the gold, right? So then the release of proteins by engineered proteins the release of engineered proteins is about 4% after 30 degree, which is not good, but it's not bad, right? 30 degree. Some people would be exposed to 50 degrees for cancer treatment, right? So definitely it's in the market within the target, but we can do a lot better than this. And this is just an illustration to show the difference between silica versus gold silica, because there's local enhancement of T2, which help to break the DNA strand. I'm almost there. So there are other people all over the world. I just show you a few recent papers, right? So there's X-ray generating gas. There's X-ray with MOF, right? So interacting with MOF to generate ROS. There's scintillation, right? So there are all sorts of work that's being done. And so I will cover a couple of things that I've done. So we've done catalysis using a gold-coated silver, and we put aniline on the surface and form polyaniline. We can detect with surface-enhanced Raman, right? So this is being done. So we've observed chemical enhancement, and then we can combine the chemical enhancement. Then we can combine chemical enhancement with physical enhancement and demonstrate that the magnitude of these two enhancements in this case is multiplied, right? That's because physical enhancement increased the dose rate and chemical enhancement is dose rate dependent. Therefore, when you have chemical enhancement and physical enhancement separately, they have two magnitude, and if we put them together, it's different. So then we prove its multiplication. So certainly we can do physical, chemical, or biological enhancement, and then we can combine that and then do other things. There are other effects we have not looked at it, but they will be useful if we go into biological systems with X-rays. So there are many products we can deal with or produce. We can develop this instrument. We can make dosimeter using materials. We can drive X-ray polymerization and charge separation. And certainly this is just one set of applications. So the work is done by my students, postdocs, and so these are my students graduated, right? Davidson and Sharma, and works for FDA now. Stark Wolf works for a big company as their vice president, and I think Yao went to Harvard. Dr. Liu and Dr. Lin is my postdoc right now. So SF funded my research, and so I'm so grateful for the National Science Foundation of the United States, America, and DOE and UC Davis, and also California Cancer Research Coordinate. So thank you very much again for the invitation, and I appreciate your invitation, and be happy to answer any questions.
Yes, any questions? Any questions to Dr. Tingua?
Thank you.
Yes. Yes. Thank you very much, sir, for participating in this event. On behalf of Organizing Committee of Chemistry Congress 2021, we want to thank you for insight presentation.
Thank you.
Yes, looking forward to meet you again next time, if it's possible in physical event. Yes, the last talk of the today's session will be Dr. Cyprian Mihai from Central Toxicological Quiver from Canada to join the event and start presentation.
Yes, can you hear me?
Yes.
I suppose you see me as well?
Yes.
Right, okay. I will share my screen and then I will turn off the camera. Is it working? Can you see my presentation?
Just we can. Yes, sir. Just you can enlarge
Yeah.
it.
Is it working?
Yes.
Yeah, okay, so you can see the presentation.
Yes.
First of all, thank you to the organizer for having me. Thank you for the introduction. My name is Cyprian Siertu. I'm coming from the Quebec Toxicology Center, Centre de Toxicologie du Québec, which is located in Quebec City, Canada. So today I will talk about the analytical approaches and recent progress in the characterization of nanoparticles in biological samples. And you will understand why I'm interested to biological samples. So first of all, I have to make a statement that I have no financial interest and I receive no royalties or research grants from any commercial company. So here is the outline of my talk. So I will first present the objectives of this presentation. Then I will explain why we analyze or we need to analyze metal nanoparticles in biological fluids, which one we focus on, how we can analyze them, and I will end up with a conclusion. So as I said, there is some objectives, some goals of studying what I'm presenting here is the first of all. So I want to give you a brief presentation of current and emerging technologies, which allows to characterize metallic nanoparticles in biological samples, and I will emphasize on a single particle ICP-MS, so SP-ICP-MS technique. Then I will discuss in details with a few examples about the analysis of different nanoparticles like gold, silver, and titanium dioxide in blood and urine samples, of course, using single particle ICP-MS. As you know, nanoparticles are now finding application in all the fields. Going from food and beverage to energy, safety and defense, as well as biomedical and biotechnology, electronics, and so on. So almost all fields are now using nanoparticles and nanomaterials. This widespread use of nanoparticles comes from their outstanding physicochemical properties like optical, chemical, electrical, mechanical, and others, thermal, magnetic, and catalytic. And this, of course, these are there is a few characteristics which explain these outstanding properties, like, for example, the high surface area and high surface to volume ratio, as well as the quantum effects. These effects decrease with the size, so give them some outstanding properties. Beside the opportunities that nanomaterials and nanoparticles exhibit, safety concerns have recently increased due to proliferation of nanomaterials and, of course, unknown toxicity of these nanomaterials. So there are growing concerns about the risk and safety when using or being exposed to nanoparticles and nanomaterials. Occupational and public exposure may occur from anthropogenic as well as environmental sources, right? Among this scenario, for public exposure, for example, biomedical application and consumer products or pollution are the most plausible. Workers also can be exposed, either from the production or pollution. The exposure ways includes inhalation, injection as well, and permeation. Inhalation is believed to be one of the most common way for human exposure. The size of nanoparticles will ultimately determine to what extent nanoparticles enter, deposit, or move to other sites in the body. Many toxicological studies have been done so far, and much is still required. But the main findings findings can be summarized as follows. Nanoparticles distribute into organs, either in blood, liver, lungs, spleen, and so on. Can activate also membranes receptors. Nanoparticles may enter alveoli, pass biological barriers, even the placenta and blood-brain barrier, and even enter cells or bacteria. Toxicology of nanoparticles might differ from different cell types and nanoparticles. And also, it's known that an important role in biological activity and toxicology is played by the surface, the high surface of nanoparticles, the area, the type, the chemical composition, and surface modification. There are many properties which characterize nanoparticles in a certain media, like size, shape, size distribution, composition, concentration, and others. Here are depicted only the most important. These properties influence how they behave in the environment and biological media, and therefore what the route of exposure and quantity of exposure might be, as well as their toxicity, of course. Risk is estimated from a combination of exposure and toxicity. An understanding of toxicity and dose allows companies, regulators, and individuals to assess risk associated with the use of nanoparticles. But which one are the most encountered in our life? For example, titanium dioxide is one of the most used in different applications, either in solar panel, in toothpaste, in food, as well as anti-scratching agent. Silver is also one of the most employed nanoparticles, especially for its antibacterial properties. We also use zinc oxide or titanium dioxide in sunscreen, and there are few applications of nanoparticles, oxide metal nanoparticles in chemistry and analytical chemistry especially, and environmental application of cerium dioxide, iron, and silicon oxide, and so on. How we can analyze nanoparticles in biological fluids? Well, we all know that there is plenty of techniques which allows to analyze nanoparticles in their raw state, either microscopy, spectroscopy, or chromatography and related techniques, as well as fractionation. For example, if you want to analyze to determine the size or the shape and dispersity of those nanoparticles. If we are interested in determining the chemical composition or we need to get some structural information, we'll either use X-ray spectroscopy or microscopy. But other techniques like BET, Auger electron, and Mossbauer also are very used. Finally, if we want to get information about elemental composition and concentration, for example, we can use either mass spectrometry in different ionization modes, as well as chromatography and related techniques like size extrusion chromatography, hydrodynamic chromatography, capillary electrophoresis, and so on. And other more simple techniques to count particles also exist, like CPC or SMPS. However, when applied to biological fluids, which are quite complex media, these techniques all show some limitation, either analytical from the resolution, for example, limitation in resolution, detection limits, dynamic range in size or concentration, or selectivity and sensitivity. Sample preparation can be also a main background, because this could bring some alteration and artifacts which will under or overestimate the size or properties. Despite the techniques that I have mentioned, which are quite widespread, these techniques are ideal for simple media, like for example, raw material or water, pure water, but are more or less compatible with liquid samples, for example, thus using high vacuum. Some of them are very costly. Some specialized equipment is needed, or scientific expertise, and others are just time consuming. Regarding the analytical challenges, we need techniques and methods which are able to give as much as possible information, so a high number of physical chemical properties in the same determination, in the same measurements. We also need very selective and sensitive techniques in order to characterize nanoparticles and nanomaterials in complex media. They should be able to deal with heterogeneous samples, which is not the case with most of the samples, the techniques. And we need to be able to validate analytical techniques, analytical methods for the detection, quantification, and in situ characterization of nanoparticles. One of the most promising technique and emerging technique is single particle ICP-MS, inductively coupled plasma mass spectrometry, which is a relatively new technique. It's based on inductively coupled plasma mass spectrometry, so it's an inorganic mass spectrometry technique. The principle is very, very simple. As in any ICP-MS instrument, a nanoparticle, which is a metal or metal oxide nanoparticle, is vaporized, atomized, and ionized into the plasma. This will generate pulses. Pulses, the technique has a few premises which stand on. So the number of pulses per second is proportional to the nanoparticle concentration, or the nanoparticles, the number of nanoparticles into a certain volume. And the pulse intensity, the intensity of that pulses we can see on the diagram, is proportional to the mass. So this will allow us to determine the size of nanoparticles. Of course, we need to know what's the transport efficiency, and we can determine that. Here are a few equations which links the concentration to the diameter or the mass of the nanoparticle. And if we have to think to an unknown samples, the characterization or the determination is very simple. First, we have to build a calibration curve, which is just simply the link between the concentration and the instrument response. Then we determine the mass flux from the calibration curve and the analyte mass in the plasma, of course, knowing the transport efficiency. And finally, we can determine the nanoparticle size from the pulses. So going through the nanoparticle mass with the mass flux and calibration curves, which are previously determined. There are a few advantages of this technique. First, it allows to determine the size and size distribution, the number concentration, as well as the composition, the agglomeration state of the nanoparticles. Most important is that it allows to determine nanoparticles and ions simultaneously. It works basically with a calibration curve, which can be done with either nanoparticles or ions. And it has a good sensitivity and selectivity, as well as high throughput. The main disadvantages is that it applies for spherical inorganic nanoparticles and has some limited resolution, as well as a high cost, because it involves an ICP-MS instrument. It allows to determine the fate of nanoparticles in a certain media, either to study the dissolution or the stability of those nanoparticles in a certain media. For the example I am going to show in the next slides, the experimental protocols has involved a spike of real matrices, so urine or blood, with nanoparticle standards, mixed or sonicate, then sampling and dilution, and finally the analysis and data acquisition with Syngistics nano application module, and of course reprocess of those raw data. Here is an example of a silver calibration curve in urine. We have both a calibration curve based on ions on the left side, as well as nanoparticles. So if we can have access to well-characterized nanoparticle standards, we can build a calibration curve based on nanoparticle size. And here is the determination of silver nanoparticles, 40 nanometers nanoparticles spiked in urine, either based on calibration, nanoparticle calibration on the left side, as well as ionic calibration, which allows to determine about the same mean size. We also have here an example of gold calibration in blood as dissolved, so ionic calibration as well as particle. Since these nanoparticles are available as standards with well-characterized standards. And again, 30 nanometers gold nanoparticles can be determined, measured in blood, either with ionic calibration or nanoparticle calibration. And we again get very comparable results. Then we study the stability of 60 nanometers gold nanoparticles in blood. This is a distribution, a particle size distribution at T0, at 0 days and after 3 months. So we were able to determine the stability of those nanoparticles in blood. And either for 30 and 60 nanometers, there was no change, no significant change in the size. So this allows to say that we have a good stability over 3 months with gold nanoparticles in blood. The same experiment has been done on urine. We have used either a urine calibration curve or a blood calibration curve, and with both we get the same, about the same size, mean size, as well as concentration, which showed the fact that no matter the type of calibration curve, either ionic or nanoparticles, or no matter the matrix used, we can get reliable results, which means that there is no effects or no matrix effects showing here for the determination of gold nanoparticles. We also did a test for the stability of gold nanoparticles in urine, and we have seen no significant change in size, so we can claim a good stability over 3 months. We're also interested to titanium dioxide nanoparticles, especially in urine. So this is the main matrix for excretion of nanoparticles, of titanium dioxide nanoparticles. So this is I would say the raw data, the spike I have talking in earlier. This is the spike we can see when we have nanoparticles in urine. This is done with NIST standard. So we simply spiked those nanoparticles in urine and got a lot of spikes, as you can see here. Based on ionic calibration, we can determine the size and the size distribution of those nanoparticles. And we compared in urine and water, pure water. But the main challenge with analyzing nanoparticles, especially titanium dioxide nanoparticles, is the agglomeration and sedimentation of those nanoparticles. And for that, so we need to improve the stability in the suspension. And we worked with different dispersion media. And we followed the size or the most frequent size and the average size, depending on the studied dispersion media. So we compared water, polyethylene glycol, polyvinyl pyrrolidone, and other PVPs, polymer of different mass. And as you can see here, the best results were obtained with PVP at a concentration of 2%. And this has been used for the further experiments. This allows, this polymer allows a good stability, and there is no agglomeration seen over time in this media. Of course, the polymer stabilizes the nanoparticles and bring some hindrance effects which do not allow nanoparticles to agglomerate together. We also test the way to disperse nanoparticles in the media, and we compare sonication bath with a sonication probe. And we figure out that the sonication probe is much more effective. It allows to stabilize, to disperse and stabilize nanoparticles within 2 minutes. So it's very quick, and the disadvantage is that each sample has to be stabilized individually instead of instead comparing to a bath, which allows to treat a higher number of samples at the same time. And then we assess the human exposure of to nanoparticles, so by measuring titanium dioxide in urine. And we used, so again, different media to stabilize them. And we came to the conclusion that polyethylene, that PVP is the most effective. So as we can see here, we monitor the evolution of nanoparticle size, the spike number, the dissolved titanium concentration over time in different media, stabilization media, with sonication probe. We also compared this stabilization protocol that we applied to different type of nanoparticles. So we have optimized our protocol with NEST 1898 standard, but we also applied to different type of nanoparticles, commercially available nanoparticles. And we can see here a comparison of size distribution and mean size for different type of nanoparticles, commercially available nanoparticles. We assessed human exposure in urine. So for that, we develop and validate a method, a method to determine, to measure nanoparticles. Here are a few parameters that we validated for urine, for example, limit of detection, quantification, linearity, so the dynamic range, the fidelity, recovery, and robustness. We also, as I said, we're interested to determine the detection limit of the method. And for that, we compare different methods to determine detection limit. The literature is quite interesting, because there is not only one way to determine, but there are different methods, and we compared all these methods for the same compositions, the same type of nanoparticles, and we also compare it with the literature, with the data available in the literature. You can find more details in this paper that we recently published in Analytical and Bioanalytical Chemistry. As I said, so we did a full validation. We also determined the repeatability, reproducibility, and trueness of the method. The robustness testing we also done, as well as the range, the linearity range that we have determined. And this brings me to conclusion. So first of all, I think I have shown that it's clear that we need to characterize metal nanoparticles and assess human exposure, and this in order to better evaluate the safety and the risk when exposed to those nanoparticles. Single particle ICP-MS looks like a very promising and a great potential for characterization of nanoparticles, especially in biological fluids, blood and urine. SP-ICP-MS has a lot of advantages, so it allows to determine the size and size distribution, number concentration, as well as composition, agglomeration, the size and ions. It allows to measure ions simultaneously. Sometimes we can easily use ionic calibration to run all the experiments. It's also very sensitive and selectivity, since it's based on the mass spectrometry techniques, and has high throughput, especially for a laboratory which provides analytical services. As disadvantages, I have to mention that for now it applies only to spherical inorganic nanoparticles. It has a limited resolution. For example, if you mix 5, 10, 15, and 20 nanometers size nanoparticles, depending on the type of nanoparticles, you might not be able to separate them or to have distribution for all these sizes. But in some cases, especially with gold nanoparticles, we can go up to 5 nanometers resolution. So this allows easily to separate them and to see distribution for all the mentioned size. It also it should allow us to detect multiple elements at the same time. And now the progress of the techniques, the developments allows to determine 2-3 elements at the same time. But ideally would be to have more elements in order to be able to determine the spectral signature of each nanoparticles. And another disadvantage is the cost, the high cost, as I said at the beginning. I would like to acknowledge the organizer of chemistry and nanoscience conferences, giving me the opportunity to present here a few results on the analysis of nanoparticles using single particle ICP-MS. I would like to thank Samantha Salou, my PhD student, which did the study on titanium dioxide nanoparticles, and the National Institute of Public Health from Quebec City, as well as the audience for your patience. Thank you so much.
Thank you very much, sir. Any questions? Any questions to Dr. Cyprian? Any questions?
Should I understand there is no question?
No one's asking the questions. Yes. Thank you very much, sir, for participating in this event. On behalf of Organizing Committee of Chemistry Congress 2021, we would thank you for your presentation. Looking forward to meet you again next time.
Thank you.
Yes. Thank you very much to all the participants, those who joined this webinar chemistry event during this period, having different different time zones. Our most sincere thanks to all the keynote speakers, plenary speakers, delegates, media partners who have joined from different destinations around the globe for this support and cooperation. Let us thank speakers who have responded so well to our invitation to participate in this conference. We have received several papers which will form the basis of our destination in the various sessions. Let us thank all the association with this conference by your presence. A special thanks to Program Manager Miss Lara Christian for her continuous efforts in putting us together under one platform in this online event. Economic keynote lecturers from Dr. Wesley Lustig from Vijaya Shilvendra, Dr. Chai Wuhova, and organizing committee members of this event, Dr. Osaman Adiguzel, and as plenary speakers, Dr. Ruben Mas Baleste, Dr. Johanna Depuche, Dr. Geoffrey Mitchell, Dr. Tingo Gua, Dr. Cyprian, and not the list. Especially we thankful to Dr. Gaikok Chomawanian, Dr. Vaktahang Barbezuo, who had joined this event from starting onwards. We will send you official through electron certificate as ebook through within couple of days. Kindly note we will start the tomorrow session by 7:50 GMT time. Finally, we extend our appreciation to each of you for your participation in this online conference. Thanking you. Once again, have a nice day. This is signing off, Madhu Bhupati.